I'm going to go ahead and get started. If somebody can type to Kim if she can't hear, to just go ahead and restart. Okay, good. All right, thanks, Kim. All right, so what we're going to do is we're going to talk about a couple of different topics, and then we'll get into the review of the CPK videos that you watched either last night or this morning. Go ahead and give me a TU if you was able to watch the 3 videos. Give me a TD if you did not. Beautiful. Looks like everybody got to see, and Erica said 2.5. Juan, did you get to watch any of the videos? Okay. And part of the second one? All right. We'll try and make sure that those that did not complete them have an opportunity to finish them up. It's going to be very important for our discussion. It sets a really, really good foundation, and you know, I'll elaborate a little bit on those videos. But seeing all 3 of them is really kind of important to the discussions that we're going to have, not only today, but leading into the rest of this course. And so, having said that, I want to go back to this discussion where we left off yesterday, and we was talking about the Box and Whisker Plot. And I told you, you know, it's a really good graphical tool. And what we established yesterday is, you know, there's quite a few people that have used Box and Whisker or have at least been exposed to it, and that's good. I want to demonstrate the usefulness of that tool from a graphic analysis perspective, and being able to tell your story or being able to analyze what the story is with the data. And we'll look at Box and Whisker Plot again later on during the course, but for this initial preview, what we're going to talk about is how to set it up in the first place. So if you had a set of data like what you see up here, the first step is to rank order that data. And so, you know, you would do this in Excel or what have you, you know, rank order your data. And then you locate the median. And you can actually hand draw this out by, once you find the median, you find the lower quartile, which is the first 25% of the data falls beneath this point, and then the median, and then the upper quartile, where 25% of the data falls above that point. And so from here, you have the first quartile, second quartile, third quartile. That's already starting to express a lot of what's going on within your data set. And what you can start to see is we create a box around this information. You get to see where the median is. Okay, so that is your 50th percentile. And then you get to see, is there skewing going on? And that skewing would be driven by how much of a range is, you know, present from like 8.5 to 12 versus 12 to 14. Okay, and so that degree of range is going to tell you, you know, whether you're symmetric or whether you're skewed. Now, in this situation, we would call this negatively skewed. If the box was taller on this side of the median, then we would call it positively skewed. And so when you start looking at it graphically, and again, whether it's in a vertical orientation or a horizontal orientation, we're going to look at a couple of different examples later on in the course that'll show you. In fact, this video will show you both, you know, analyzing some data with vertical orientation and horizontal orientation. But either way that is presented, this already starts to tell you a lot of information visually. If you have different X drivers down here at the bottom that you're analyzing, then this grouping of data represents very high on the Y output as compared to this grouping and this grouping, moderately higher than this grouping. And so again, that already starts to tell you a lot of good information. But you have a lot of skewing in this data set. You have a lot less skewing in this data set, except for, you know, you got a longer whisker here on the bottom, but that's not always a big deal. Where it starts to become a big deal is where you see these asterisks. These asterisks are representing outliers to your data set. And so within this data set, there's an outlier in the negative side. And within this data set, there's an outlier on the negative side as well. And so that starts to tell you, you know, again, like I say, just one picture, you know, can tell you a whole lot of information. Now, how relevant is this information? Well, that depends on what we're mapping. You know, how relevant is this degree of variation? Again, that's all driven by the specifics of what I'm mapping, what my scales are here on the y-axis, and things of that nature. But, you know, if you ask me, hey, are these groupings on the X driver, are they performing equally? And the answer to that is just by visual inspection, no. But then we can step into other hypothesis tests that we're going to cover during the analyze phase. Is we'll step into like an ANOVA, because I have 4 elements here, and I'll see, you know, is this difference of statistical relevance? That's what my ANOVA, analysis of variation, is going to tell me. And I'm pretty confident that if I ran an ANOVA on this, depending on what the scale is over here on the y-axis, but if I ran an ANOVA on this, I'm going to find a difference of statistical relevance. So we'll experiment with that once we get into the analyze phase. Right now, I just want you to understand, you know, the power really that you have with just graphical analysis using this box plot. Now, this, I already told you, you know, the bottom of the box is your first quartile, where you see a difference in the shaded colors here. That's your second quartile. Then your third quartile is up at the top of the box. The way that the length of the whiskers get determined is if you have a data element that is within 1.5 times the interquartile range, the IQR, the interquartile range, it will extend a whisker out to touch that point. If you have no data over here, or if you only have a data element like say at 15, then the whisker would be that short. But the whisker will be allowed to go as far as 1.5 times the interquartile range. Anything that goes beyond that becomes marked with a star or asterisk in the software, because that is considered to be an outlier to your data set. And you could have multiple stars and asterisks. Let me get into the video.
The box and whisker chart helps us analyze variation across multiple things. These could be injection ports forming plastic bottles or something like that. And so what you need is some data. And here we have injection by cavity. Click on QI macros box and whisker. It'll ask if you want to group it by row or by column. We're going to go column. And here you can see we have our medians are slightly off from cavity to cavity. We might like to align those to get a more consistent product. We could also take this data, click on box and whisker, and group it by row. And that might tell us something about tops are doing one thing and middles are doing another, and so on. And so this would be a way to start to analyze variation in your process using the QI macros box and whisker plot.
Okay, and you don't have to have QI macros to do box and whisker plot. You know, there's a variety of different types of software that can give you box and whisker plot, and you could actually build it yourself. But you know, I'm not a graphic artist, and so I don't like to build these charts and graphs and things of that nature. And so And I don't like to monkey with something that's really going to cause me to have to do a lot of interface to create the graphic or to refine the graphic. I like some software tools that, I select the data and it presents the graphics instantaneously. If you don't have that, work within your organization and gain access and gain knowledge and understanding and familiarity with software that produces graphics and does statistical analysis very user-friendly way. I'll show a couple of demonstrations with the use of Minitab. Give me a TU or a TD if you've used Minitab before. TU or TD? Okay, I'm going to show a couple of demonstrations with Minitab because around the world, Minitab is kind of like glued to the hip with Lean and Six Sigma, and IASSC and ASQ both heavily embrace and represent Minitab in their body of knowledge, and the graphics that they display in their body of knowledge, and then the graphics that they display on exams and things of that nature. And so I would like you to see some of the graphic outputs from Minitab and some of the functionality with Minitab. And if you had to ask me 10 years ago, is Minitab worth having? The answer would have been no, because it was extremely clunky and not user-friendly. Now, it depends. Are people in your supply chain using Minitab? If they are, it helps to be consistent with what other organizations in your supply chain are using. And other than that, for those of you that are using things like Tableau or other software already within your organization to do this statistical analysis, then fine. Use those tools. If you need to get something for your personal computer and you're going to have to flip the bill for it, that's where I start directing people to, get the bolt-on macros like what QI Macros has available for you. All right, so scatter diagrams. Just about everybody in here should be familiar with and know how to populate a scatter diagram with relative ease. And because this has been around for so long, and so obviously if we're looking and we're assessing whether something has correlation or not, what we're looking for is to say that it has positive correlation. As I increase across the x-axis, I'm also increasing across the y-axis. Negative correlation, obviously, as I increase across the x. As I increase across the x-axis, I'm decreasing across the y-axis. So that's my negative correlation. Then, of course, we would represent this as being no correlation at all. And that's all fine, but it's scatter diagrams in and of themselves without a Pearson correlation coefficient being applied to it, and in other words, give me an R value, a rho value, without that value being assigned to it, it all becomes very subjective. Now, if the data is very straightforward and it's like what you see plotted here, and you can make a quick, ready assessment, yeah, that's pretty much a straight line there, and it's good. But then when you get into presentations like this, to where it's not as obvious that that's a good linear line there. Now we kind of have to make a decision, well, is it good enough? Yeah, it looks like a positive correlation, but is it good enough? Because it's not as strong, it's only a moderate positive correlation. And so the point that I'm making here with these scattered diagrams is we would say that this has no correlation, but a lot of that has to do with what are my scales here on the x-axis and the y-axis, and could I trick it out? Could I make something that looks like a moderate correlation look like it has no relationship at all? Well, that's pretty easy to achieve. If I dramatically increase or decrease the scales on my x-y axis, then I can either spread out that data or I can shrink it and make it look closer together. And so I don't like looking at scatter diagrams to establish whether there is or is not correlation without the advantage of having an R value there. And if I'm going to bother to get an R value, then why not bother to just go ahead and do a regression analysis? Because if you're going to calculate for an R value, you're probably using some data pack, some data software, you know, to give you the Pearson R value. And so if you're going to bother to push that button, why not just do a regression analysis? And when we get into regression, you know, I'll get into, you know, expressing how much better regression analysis is rather than just looking to see if something has correlation. There's an expression, correlation does not prove or constitute causation. And that's very much true. Now, you can have some of the same argument with regression analysis, but because of the math that's associated with like simple linear regression that we're going to demonstrate here a little later, is because of the math that's associated, I'm creating, you know, a predictive value, and then I'm going to develop my R square value, you know, my coefficient of determination for my R value, and that is really a lot more powerful because what I'm looking at is I'm looking at the errors and the calculation of the errors from this supposed fitted line, and I'm creating a predictive formula for predicting, you know, hey, if I have a future X data point, you know, where is it going to fall? Well, that's going to be based off of a regression equation that we developed through that process. So again, scatter diagram, yeah, you can get a quick look, but you can also fool people with that quick look. So have at least an R value to base judgments off of. But if you're going to push that button, push the regression analysis button instead. And so we'll get into some of the math that's associated with this once we get into regression analysis. We're just looking at some of the graphic interface right now. And I'm sure everybody here is familiar with histogram or bar charts, you know, so bar charts, you know, would represent like this, and I got categorical data typically down here on the bottom, and it tends to not be continuous data that I'm representing with my bar chart. And so what looks very close to that is this histogram. It is actually continuous data that I'm representing. Now, I can represent discrete data as well with this histogram, but the whole idea is if you see gaps in here, it just means that data is not present within that zone. Whereas, you know, with my bar chart, you know, I'd have specific drop buckets, and it's intended graphically to have the gaps in there, just kind of let your eyes follow along the distinctions in the categories there. Now, getting into the further into this discussion about, you know, scatter diagrams and kind of upgrading that tool use, what I'm really trying to do is I'm trying to figure out, you know, do I have normal, do I have a normal probability, you know, chance of success? If I say that something has a linear relationship, like say I want to say that it has a positive correlation or a negative correlation, will it pass muster on a hypothesis test for normal probability? And so to demonstrate normal probability plot, we're going to use this video, and there's going to be a demonstration doing it straight in Excel, but then we'll use an example using Minitab. So first we'll look at normal probability plots, generating normal probability plots with Excel.
If you work in a team, you should be using Monday.com. It's a platform to manage any team and any workflow, marketing.
This is Stephanie from statistics.Com. and in this video I'll show you how to make a normal probability plot in Microsoft Excel. The first thing we want to do is type in our X values. It's in column A. I want my values in ascending order, so I'm going to highlight the column, click Sort and Filter, sort smallest to largest. So my values are now from smallest to largest. In the next column over, we just want the position. We need this for the formula. So I'm just typing 1, 2, 3, 4, 5, 6, 7. I have 7 values. If you had 5 values, you'd just type 1, 2, 3, 4, 5, and so on. And the next column over, we want f sub I. That is the formula down here. F sub I equals I. I is the position minus 0.375 all over n. That is the number of items in our data set. We have 7 items plus 0.25. You can get Excel to calculate this formula for you. Type equals. We have I, which is this position here. I'm going to open parentheses, click the first cell in the B column, and then minus 0.375, close parentheses. Divided by, we have n, 7 items in our data set, plus 0.25. Open parentheses, 7 plus 0.25, close parentheses, press enter, and that is the first number in our formula. I could repeat this for every cell, but instead of repeating the formula over and over again, I'm just going to grab the fill handle in the bottom right and drag it down to the last cell. And here's our F sub I values. The final thing we need is the Z value. You can do this with a built-in Excel formula, equals NORM. Choose the NORM SINV option. In other versions of Excel, you might see this as NORM.S.INV. Double click. We want it to calculate the Z value for these F sub I values. So click the cell that has the F sub I formula, close parentheses, press enter. And again, I'm going to drag my fill handle down. And that has filled in all the values for me. The last thing I need to do is create a scatter plot for my X values and my Z values. I'm going to click A to highlight column A, hold the control key, and click column D where my Z values are. So both A and D are highlighted. Click Insert, Scatter, Scatter with only markers. And here is my normal probability plot for that set of data. Check us out at statistics.Com for more videos and articles on everything elementary statistics. This is Stephanie from statistics.Com.
Okay, easy to do, right? What's the problem here? Do you see a problem? What if you had to do that over and over again yourself, or have other members on your team doing it? Is there a potential problem that's going to arise? User error, very much so. And so it doesn't matter if you're using well, it doesn't matter what software you're using, so long as it's good and reliable software. They're all going to function the same way. This is why we want to get out of Excel native, and we want to be working with macros that are bolted onto Excel, or we want to be using dedicated statistical analysis software. Because that old school way of doing things, it's not reliable.
Most homeowners insurance providers can give you a quote online, but you know what they can't give you online?
This is Stephanie from statistics.Com, and in this video I'll be showing you how to make a normal probability plot in Minitab. I've entered my data into 2 columns. The grades are my categorical variables. I've got 9th grade through 12th grade, and the GPA is my quantitative or my numerical variables. That's the spread of GPAs in the grades. Click Graph, Probability Plot. Choose the single probability plot. And I want to graph my GPA as the variable. So click GPA, then click select. That moves GPA over to the graph variables box. Click OK. That brings up my probability plot. Now it looks like my grades, my GPAs, are approximately normal, which is what I would expect from a GPA, but could be a little bit skewed, especially at the top and the bottom. So to get a better idea, I'm going to go.
Okay, and so what we're looking at here is we're looking at, do things fit close to this this fitted line? Do they fit within the bands, or does at least the majority of the data fit within those bands? Well, if that's the situation, then your p-value is going to pass muster. It's definitely going to be above a 0.05, you know, if you're within these bands. Now, the p-value of 0.732, it depends on how reliable I want that that outcome to be. Now here you see we have some things that are kind of popping out towards the outer bands, and so this p-value is suffering just a little bit for the amount of data that I had here. If I had a strong cluster, you know, say I had 1,000 data elements in here or 100 data elements in here, and then you know I had, you know, a few popping out towards the band, the more that I have in the concentration close to the fitted line, the more that it's going to tolerate some of these exceptions. And even if I go outside of the band with a few of them, if I have a very strong, you know, population of data elements that are really close to the fitted line, then it's going to kind of excuse those and come up with even a higher p-value. If I'm looking to be extremely confident that I have a really good normal distribution with that data, then I'm looking for things that are typically 0.80 and above, and we'll use the same expectation when we're looking at regression analysis and looking for our square value of 0.80 or above. This one, it's pretty good, and we'll look at what it looks like in a histogram format.
Go ahead and make a histogram. Just going to choose a simple histogram. I've got my GPA as the variable. You can see it follows an approximate normal distribution, but it's a little uneven in places. I wouldn't say that this set of data is approximately normal. I've got another set of data of GPAs here. It's slightly different. I'm going to click graph and probability plot. Single again. I'm graphing the exact same variable, the GPA. And this time you can see it fits closer to a line. It looks like it fits a normal probability distribution a little better than my last set of data. So I'm just going to go ahead and check the histogram. And there you can see it's much closer to a bell curve, so it's not surprising that the normal probability plot was closer to a straight line.
Okay, and in this situation, the categorical data, you know, was represented as 9th, 10th, 11th, and 12th graders. And if I found out that my data, you know, didn't follow any kind of normal probability, and I want to do some normal probability analysis with my data, then probably what you're going to have to do is go back into your categorical data and stratify this data. And what would be logical would be to stratify the data by grade level, and then, you know, look and see, you know, does that you know, present itself as normal distribution. And then if you're curious why there's a difference between 9th, 10th, 11th, and 12th grade, or if that difference is of statistical relevance, once we have that data stratified, we can do additional testing. Right now, all that we're doing is seeing if it follows normal distribution. Once we get data into sets that follow normal distribution, then we can do some normal distribution hypothesis testing. If our data is not going to follow into normal distribution, I'm going to keep the same type of grouping of data and doesn't follow normal distribution, it just means that I need to use non-normal hypothesis testing tools as opposed to the normally distributed hypothesis testing tools. So I'm going to use some non-parametric as opposed to parametric. And again, we'll get more into that in the next phase when we get into analyze. Now, before I step into this conversation about gauge R&R, because we're going to have an exercise associated with that, I need to check and see if we have everybody here now. Is Trinice with us now? Trinice, are you able to hear me?
I don't see her name in the screen.
Okay, that's fine. We'll give her a little more time before we get into the actual exercise associated with measurement system analysis. Yeah, okay, thanks, Kristen. All right, we'll give just a little bit more time before we actually get into an exercise, because I want to do a little group exercise associated with attribute gauge R&R. But first, we'll look at the overview videos for gauge R&R and what it's really about, and just kind of open the floor for discussion. Give me a TU if you've used gauge R&R, or if you've studied gauge R&R, or you have an idea of the concept. Give me a TU or a TD. Okay, and that's not entirely surprising, because a lot of times gauge R&R is a tool, is a methodology of measurement system analysis that's used more often in physical flow environments, like if you're in manufacturing or supply chains and things of that nature, as opposed to the nature and the type of business that you're associated with. But however, having said that, attribute gauge R&R could be of advantage to your organization for challenging your ability to determine consistently whether something is good or bad, pass or fail. And it's not so much in the measuring side. When I'm doing measures in a physical domain, we're going to use the variable data gauge R&R tool set. But if I'm just making a decision if something is good or bad, or passes or fails, or accepted or is rejected, then I'm going to use the attribute gauge R&R. So we're going to do a little exercise actually using attribute. We won't do the exercise using the variable data. But basically what we're looking for with gauge R&R is we're just going to run a test with gauge R&R to determine if the people that we have in place in our systems that are making critical decisions, whether something is good or bad, passes or fails, whether they're able to do that consistently, and first and foremost agree with themselves in their analysis. But then importantly also is if you have 2 or 3 different appraisers, do those different appraisers agree with each other? And so whatever it is, even if it's a form or a document or an entry on a form, whatever we're analyzing, within our systems, is it good or bad? Should it be passed or should it be rejected? Then we can do this type of a study. Now, unfortunately, ASQ and IASSC, they think that gauge R&R is all that's out there for measurement system analysis. And the evidence of that is their body of knowledge is just chock full of gauge R&R stuff. But in reality, as a practical purpose, it's not going to fit every problem that you have or every organization. And so my answer to that is just look at more of an expanded view of what gauge R&R, or what we're really trying to do in measurement system analysis. Measurement system analysis, we're trying to validate that wherever we're collecting data and wherever we're making decisions on the values of that data, that we're doing it consistently and that we're doing it with agreement. I do need to give you all this material though, because, or at least an overview of all this, because you will have some questions on your test regarding this. All right, so we'll just start off with the basics here, the what is gauge R&R.
So what is measurement systems analysis? Well, you know, we know in our root cause analysis that things can be caused by process, machines, materials, people. But one of the contributing factors, especially in manufacturing, can be your measurement process. And so we have to find ways to measure and confirm that we're good. We have a good method for measuring things. All right, so the way we do that is with gauge R&R, linearity, and bias. And so when we're measuring things with a gauge, I mean, it's pretty simple, right? We're going to be measuring things. So we can measure variable things like length, width, diameter, time, so on. And that's where we're going to do our variable, our attribute, our average and range method, the ANOVA method, specification tolerance method. And there's also what's called attribute method, right? And so we...
Okay. On the variable where he's talking about range and average or ANOVA method, there's two different paths that we can take for the variable gauge R&R. We're not going to get deep into the variable gauge R&R for your testing purposes. I need you to know that the ANOVA method is the best method to use because it's going to give you the most accurate determinations.
We can actually have a situation where we have pass-fail gauges, where you've got a widget and that widget has to pass, you know, not through or through a couple of things so that it actually goes, yes, it passes. You know, it's not too small and it's not too big. And so those are kind of the pass-fail kind of gauges you see. So gauge R&R is a method to go out and determine, is our process, you know, for measuring good? And if it's not, then we're going to have variation.
Yeah, Kristen, I will repeat what I just said. What he just talked about was with the variable gauge R&R, you have two different types of analysis that you can do. You can base your analysis off of range and average, or you can base your analysis off of ANOVA. And it's, you know, the tools that the software is going to use in the background. ANOVA is your preferred methodology, okay, because ANOVA is going to give you the most accurate, detailed information. Is that understood, Kristen? All right, thanks.
And then bias is one of the things we want to look at. So if we're measuring here, if a gauge is measuring in this range, but our reference value is over there, the difference between those two is bias. And so bias is one of those things we want to track. Is our gauge biased on the high side or the low side? And then linearity is bias measured across the range. So imagine that I have a baseball bat here and we're measuring it from the small end up to the wide end. Does it have a way of doing that that's consistent, or does it measure a little high here and a little low there, or vice versa? And so that's what measurement systems analysis does, is help us understand how our measurement is working.
Okay, and when we're determining what the bias is in that measurement system, what we're going to do is we're going, and as he's going to present in the next video, you're going to have multiple trials taking the measurement. And so first is we're going to determine within your own performance, if you're measuring the same item 2 or 3 times, or even more times, if you're measuring the same item, whether it's time or whether it is, you know, whether something is good or bad with attribute, but in variable, you may be measuring the length of time. And if you're measuring the exact same thing over and over again, how much bias between the gold standard, what it's known or believed to be by gold standard, versus how you're measuring it. And do you have variation in your own performance? Okay, and so then we would start to, say, well, we have a repeatability issue if it's within your own performance. In other words, you can't repeatably find the same measure. And so you'll have a performance range. If I had you measure it 3 times or 4 times or 5 times the same item, and you kept coming up with different amounts, what it's going to end up doing is it's going to end up creating like a curve around your performance. And so then if I have multiple people, if I'm comparing, appraiser 1 versus appraiser 2 versus appraiser 3, then what type of bias do we have between the performers? And so we're going to look at the variation within, and we're going to look at the variation between appraisers and quantify what that degree of bias is.
Is it a gauge problem, or is it a measurer problem, right? Is the guy taking the measurements doing the right job? And so we'll get into each one of these and how to go about that. But that's the simple overview of what measurement systems analysis is designed to do, is help you prevent measurement from being one of your root causes of error.
We'll go into how to set up. Now, this is an important note if you are actually going to do a gauge R&R, especially if you're going to do it in the physical domain.
This is Jay Arthur, and one of the biggest mistakes people make when trying to do a gauge R&R analysis is setting it up improperly. The first thing you need, obviously, is a gauge. And then you're going to need 2, count them 2, appraisers, 2 different people using this one gauge to actually go measure this.
And that's a minimum standard. You need at least 2 appraisers because we need to determine if there's a difference between appraisers. And in reality, where it's possible, we want 3 or more appraisers, but the bare minimum standard is you have to have at least 2.
This equipment, all right? And they need a consistent way of measuring it. I don't care if they're measuring the inside or the outside, they need a consistent way that they actually do that process. And here's what happens. When you do this, most people are actually, when they're manufacturing, they produce a pretty good product. And so if this is their target value, one of the things you find is that they're producing parts that are pretty much perfect, all right? To do a good gauge R&R study, you need bad product, all right? You need a bad widget. You need things that span the entire spectrum from the lower spec limit to the upper spec limit. And you need at least 10 parts that go across here, all right? So we need parts that span that entire stretch from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that way, because the big issue here is part variation. Your parts have to vary enough or you will not get a good gauge R&R result. And there's actually a little thing called NDC, the number of distinct categories, which is calculated, which tells you need a minimum of 5 distinct categories. And the biggest mistake I see is people come in and they say, well, gee, I produce great parts. I should have a great gauge R&R. That's not how this works, right? You need bad parts to get a good gauge R&R reading. All right, so that's the setup. And then once you've got these 10 parts that span your spec limit, your spec tolerances, then what you do is just number them, and then you pull them out of a can or whatever it is, and have them measure that separately at least 2 times. So they have to have 2 trials. So 2 appraisers, 2 trials on each part, and that's what you put into your gauge R&R analysis. Now you can have 3 appraisers, you can have, have them try it 3, 4, 5 times, but 2 appraisers and 2 trials are probably enough to tell you if you've got a good measurement system. Because gauge R&R is really about determining, can I measure accurately? Remember, in the Ishikawa diagram, there's the 5 things that can cause problems, right? Man, machines, methods, materials, and measurement. Measurement is the 5th thing. And sometimes environment, That might be a sixth thing. But measurement can be a source of error, right? So you may think you're producing great widgets, but if your measurement system is off, then you have a problem.
All right, so we'll look at an example on the variable data side, and then we'll look at an example on the attribute data side.
One of the 5 types of errors in root cause analysis is measurement. And so gauge R&R is used in manufacturing to assist in determining whether there are problems in your measurement system. And it's pretty simple. You need at least 2 appraisers here. And you need 10 parts, usually measured at least 2 times, maybe 3, maybe more. And in this case, we're using Ford data. There's actually 3 appraisers and 10 parts and 3 trials. So in the QI macros, simply click on DFSS, gauge R&R, choose the gauge R&R form to get a blank form. Here you can see our blank form. It's ready to go. And if you open up in the QI macros, you will actually find our AIAG SPC data. And here you'll find our Ford data.
Okay, and what he's talking about in QI macros, as well as some other software packages like Minitab, there's data that's available that you can practice different tools with and stuff like that. So you don't have to make up data. Data, is already existing, and what he's talking about, AIAG, is Automotive Industry Action Group. They have a lot of data sets that you can play around with and practice these type of tools with.
So we're just going to take and copy this, and we're going to switch back over and paste that into our spreadsheet. And right here, you'll also notice that we have a specification tolerance of 2, and we're going to use that as well. Because the gauge R&R worksheet has 3 different ways of measuring gauge R&R. So here we have our appraisers, and again, normally you would just choose different, put these in random order and let people test them with the same gauge. And we're going to scroll on down here. And here you can see we can put in our spec tolerance, which is 2. Now, the thing you want to look at first is NDC. This is the number of distinct categories. That means, do you have enough part variation to get an appropriate gauge reading? A lot of people, measure identical parts and wonder why they can't get a good gauge R&R. You need bad parts to do a good gauge R&R. So your NDC should be at least 5, all right? Now, if we look at it, there's a number of ways to do this. One's called the average and range method, which is right here. And so the average and range method says equipment variation is 9%, appraiser variation is 5%. So the equipment is actually a little bit dicier than the appraisers are, and our overall gauge R&R is slightly above 10%.
Which is good. Industry standards are up to 10% is just good across the board. Between 10 and 20%, it's getting a little bit shaky. It becomes a business decision. There's some situations where you can have up to 30% variation, but that's saying, that there's very little criticality between being able to select whether something is good or bad or pass or fail. And to me, anything above 20% with a variable study, you need to reevaluate, how your appraisers are doing things. Between 10 and 20%, it becomes a business decision. So you'll hear that over and over again when you're talking about gauge R&R. It's a business decision. How critical is that? How critical is it to get beneath 10% variability? In some processes, it can be very difficult to get beneath 10%. And so are you going to get enough return on investment? Is it critical enough to you? Those are all things that you need to make determinations on from a business analysis sense. But if it gets between 20 and 30, that's very, very dicey. Anything above 30 across all industry standards, that's junk. You got a junk garbage measurement system, and you need to radically change the way that you're doing measures.
And what this says is that if our percent R&R is greater than 10%, it may be acceptable based on whatever. Or you may need to tune up your gauge for maintenance and redesign, better clamping or something of that nature. Another method is called specification tolerance. Here you can see our spec tolerance, and it's calculating that percent R&R using spec tolerance is actually acceptable. Now, in the automotive industry action group, you can use either one of these two things, and again, it depends on your customer. So there's total, that's actually using the average and range method. There's the spec tolerance method. Now, if we scroll down a little bit more, you're going to find the ANOVA method. So here's our total variation right here, without interaction between issues and with interaction. But if you look closely, you'll notice all of these are in the green, which means they're all under 10%. So I would say that our gauge using spec tolerance and using the average and the ANOVA method shows that, yeah, our gauge system is acceptable. So we're doing an appropriate job of measurement. And that's how easy it can be to do a gauge R&R study using the QI macros. And choose which one of these methods is right for you and confirm it with your customer. Make sure you have an NDC of at least 5, in this case 14, and you'll get the right answer. And if you look over at our Ford data, you'll actually see that all of these actually match the results that are obtained in the QI macros. So that's how easy it can be to do gauge R&R to determine that your measurement system is working appropriately and is not a big source of error.
Okay, and he started to scroll down and show you, the some charts and graphs that it spits out at the same time. But again, we're not going to get deep into the variable data. What we're going to do is we're going to do the example with the attribute data, which I think is going to be more useful to you and your organization. So let's see, I'm having trouble getting this to go back down. Here we go. All right, so we'll show an example of attribute, and that's going to lead us up to, well, we're getting real close to a break time, but I want to get this and get us set up for doing the exercise when we come back.
Gauges, again, can be designed so that they either give us a pass or a fail. Now, when we're not actually measuring anything, like with the basic gauge R&R template, what we need to do is conduct an attribute study of the gauges and their abilities. And in here, you're going to see places to fill in things. So we have 3 appraisers and 3 trials. You could do this with 2 appraisers and 2 trials as well. And 1 says, whatever part I measured passed, and 0 says whatever part I measured failed. And then once you've conducted these trials, you're going to want to come back and actually come up with a reference value for this particular part. And what are the upper and lower spec limits for these particular parts? Now, I've taken, again, the AIAG example. And here you see all the different reference values for a set of parts, and whether they passed or failed. And in some of these cases, you'll see where they passed and sometimes they failed. And the code here says that this is around the upper spec, minus is around the lower spec, and X is in the sweet spot between the 2 goalposts of our.
Okay, and so this reference value is what we would call the gold standard, okay? It's what they should have determined as they were evaluating. And then, if they're off from the gold standard, that's where it's going to start saying, okay, well, they have some bias in the measure.
Upper and lower spec limit. If you scroll over, it'll tabulate all of this information for you. And so here you'll see that A and B agreed on which ones failed and which ones passed, and they only missed a couple of times. Same with B and C and C and A. So you get to see sort of the dance between the various appraisers. And then against the reference value. So appraiser A had 41 and 99 correct, and they had one that should have failed, but they passed, and 9 that should have passed, but they failed. So this is how you'd start to look at and see how everybody's reading the gauge. Over here you can see the effectiveness of all 3 appraisers, and overall on the system, so our miss rate was only 7%, and acceptable is over 90%. So here we've conducted an attribute gauge study and determined that, yes, our measurement process is acceptable.
Okay, and with the attribute, you don't really, for any industry standard, you don't really want to go above 20%. With the variable, yeah, it's possible between 20 and 30. With attribute, that top threshold really is about 20. And so the linearity.
There's one more thing we might want to figure out on a gauge. Let's say you're using some sort of measuring instrument, a gauge, and you want to measure different ends of a baseball bat. One end smaller, one end's fatter, and the various points in between. Well, if we know what our reference values are, then we can start to measure that. You want to put in your reference values for different sizes of things you're measuring, and then all the different trials of that particular thing. And I've input an example here. Again, this is from the Automotive Industry Action Group. So here you see a whole bunch of things measuring 2, and the reference value for this, an actual measurement with really a good gauge, is 2 and 4 and 6 and 8 and 10. So these are your known values here, and this is where all your data goes as you try stuff. Now if you scroll on down, ideally you'd see a line that's horizontal. But as you can see here, early on, the gauge overmeasures, and as we go on, the gauge will undermeasure as the big end gets fatter and fatter. So this tells us that our gauge isn't quite as accurate as it should be over the range of possible things we're measuring. Maybe we need to get a different set of gauges or a different kind of gauge that can measure this range, or we need different gauges for each of these different pieces of this puzzle. So that's how to conduct an analysis of linearity using the gauge R in our worksheet.
All right. And so what we're going to do is we're going to go to break. And when we come back, we'll get into an example of doing a attribute study. We have a good timeline working for us right now as far as where we're at in the course and where we need to be by Friday. So let's take the opportunity to actually do a group exercise associated with the attribute, and you're going to be evaluating the quality of M&Ms when we return. And so if working with M&Ms is going to make you hungry, go ahead and grab some candy or something more healthy to snack on while we're on this break. We will return at 45 minutes after. Go ahead and give it to you if you're back and you can hear me. Waiting on a couple of people. Still waiting on a couple of TUs. Okay. And there's one more TU. Ah, there we go, I think. Okay, we'll say that's everyone. All right, and so here, what we're going to do is we're going to get set up for a gauge R&R with an attribute study. Again, I think the attribute study is probably going to be more useful to you unless there's something that you're measuring time that has a criticality of you know, being on track within seconds or something like that. And so, but by and large, I think, you know, probably what's going to be more useful to you is the attribute study, and you can study more about the variable gauge R&R that you would use for continuous data, and see if that's applicable to something that you can use in the future. But for our purposes, it's going to be a little bit interesting, you know, trying to do this in a virtual setting and kind of get everybody onto the same sheet of music. Much easier to do live in person, where we have real physical M&Ms that you're evaluating in person. But what you're going to do is you're going to evaluate the quality of M&Ms based off of this rejection criteria. And the rejection criteria that you're looking for is if the M&M is misshapen, if the M&M logo is faded or not clear, or if the M&M logo is off center from the M&M, or if the candy shell, you know, appears to be chipped. And so this is your rejection criteria. If it doesn't meet these rejection criteria specifications, then you would say, okay, well, then it's a good M&M. And I'm going to give you a peek at how you're going to see these M&Ms. We're going to have 3 rounds, and on round 1, the M&Ms are in a particular sequence that I already have knowledge of. Okay. This isn't. This is actually another vendor's trainer that kind of set this virtual exercise up. It's not my virtual exercise. However, I do have the gold standard answer key, and that's one thing that's necessary when you're setting a test up with gauge R&R. You, as the person that's running the test, needs to know what the gold standard is, and you need to have that pre-recorded. And what gets interesting with this gauge R&R is when you come back and do round 2, the M&Ms are going to be rearranged. And then when you come back and do round 3, they'll be rearranged again. And so when you're trying to control the study, knowing what the gold standard is for each M&M as it's placed, you know, is important. So you can compare the results of your appraisers to that gold standard, but be able to keep track of where you're moving the bad M&Ms and where you're moving the good M&Ms. And so a gauge R&R can be interesting. Now, just like with the variable data study, when we're doing an attribute study like this, it's going to be necessary for us to have some that are good and some that are bad, so we can pick up on the difference of people's ability to show repeatability within their own performance. In other words, if the first time they say that this particular M&M is good, and then the second trial, no matter what position this M&M is in, if this M&M they say that it's bad, and then they on the third trial they say it's good again, well, they don't have repeatability within their own performance. And reproducibility, a problem with reproducibility is if I had appraiser 1 say that this is good, and then appraiser 2 says that it's bad, then we don't have reproducibility in between the appraisers. And this kind of mounts evidence as we go through multiple trials. It kind of mounts that evidence up, you know, whether we can have repeatability or reproducibility. Repeatability within your own performance, reproducibility between performers. And the M&Ms aren't going to stay this far away. She's going to get the camera closer to the M&M, and she's going to let you actually look into the cup. And she will do that with each M&M. And she's going to give you a pretty good view. It won't be jumpy like what you see right now, but she'll give you a pretty good view of the top, the bottoms, the sides, and you'll move on. All right, now the way that we're going to collect this data is we're going to do it on a Google spreadsheet. And so what I need people to do, as I start to talk through it, I'm going to give you the link here. Go ahead and test your access to this link. Oh, that's bad. That's weird. It shouldn't. Huh. Okay. Okay, let me see if I can get into the sharing. Hold on. Okay. Please try again. I changed it to sharing. All right. It would be interesting to know who the turtle is. We have a grizzly bear. That's pretty interesting. I don't know who the turtle is. We got a kangaroo. All right. And so I think most people got in, and you know, if you can't get in individually, maybe we can have one of your teammates help you out with your data entry. Maybe somebody on your team is going to do all the data entry for your team. You know, it just depends. Now, I will say this: it's going to be important that we follow a convention when you're entering in whether something is good or bad. As you see with this results sample, I intentionally left some good entries and bad entries. And so this bad entry where, you know, you start off with a capital letter and then it's lowercase. That's the proper convention. Good. Starts off with uppercase and then lowercase. If you put it in all lowercase, or if you put it in all uppercase, it's not, the test is not going to work. It has to match this convention of start off with uppercase and then lowercase. And so this is the way we're going to have to do it. We're going to have to break into 4 teams because I have this study set up for 3 appraisers. And so I need sets of 3 appraisers. And so what we'll do is we'll have one person out of team 1 will go to team 2. Hold on just a second. No editing. Okay, Juan says he has no editing. There's somebody else on Juan's team. Oh my goodness, what is going on? This is you. I've used the same thing. I've used the same spreadsheet for others. They haven't had this problem.
I think we have to be signed into the label to be able to edit.
Yeah, but I've run this for a team exercise before and didn't have all this issue. So let me see here.
There is a settings button. Maybe there's something in there where you can allow us to edit.
Yeah, you have the access to share, and so I'm wondering where you got locked out from editing. Let's see here. Editors can change permissions and shares. Viewers and commenters can see the option. Change. Okay, here we go. Editor. There we go. All right, now just try to type anything in anywhere.
It works.
Okay. All right, good deal. All right, so now one says you need to share the link again.
No, you just have to refresh the page and it'll work.
Refresh the page. Okay.
Like us, the users, we have to refresh.
Oh, okay. You're saying they have to, okay. All right, so now you should have the capacity to edit. There we go. Mamma mia. All right, I appreciate that. And so, you know, like I say, trying to do this in the virtual space, it's a little bit challenging, but we're going to get over this hump here in a minute. All right. And so to get our teams oriented and fixed right, I'm going to need one person from team 1 to join with 2 people out of team 2 to become team 4. All right. And so 3 people in team 1 that currently exist in team 1 get to stay there. And 3 people out of team 2 get to stay there. But 1 person out of team 1 and 2 people out of team 2 need to combine to become team 4. So who are those people going to be? Okay. And so long as you know that now we have a team 4 that's comprised of 1 person out of team 1 and 2 people out of team 2. And team 3, you are just the right size. So we're going to leave you alone and all your players stay in the same place. Okay. And so here's how it's going to roll. You're going to get to decide within your team who is appraiser 1, who's appraiser 2, and who's appraiser 3. You can self-assign that within your team. And once you figure that out, then the first appraiser results will get populated here for the first trial. And then for the second trial, you will populate your results after appraiser 2 and appraiser 3 have have populated their trial 1. And so we'll have appraiser 1, 2, and 3 populating for the first trial. And then we get into the second trial. And then appraiser 1, 2, and 3 out of each group will populate their results for that second trial. And then we'll get into the third trial and the same sequence again. So what's important here is that within your group, appraiser 1, appraiser 2, and appraiser 3 has to maintain, consistent. The same person is appraiser 1 for trial 1, 2, and 3. The same person is appraiser 2 for trial 1, 2, and 3. And same person is appraiser 3 for trial 1, 2, and 3. If your team is able to, keep that sequencing proper, then, we'll get some good results. If that gets flubbed up, because we're trying to manage things in the virtual space here, I get it, and we'll get bad results, from our analysis. But once your teams, get this all populated, then we'll actually be able to take your data, your information, and I'll run it through a Minitab utility, and I'll show you the graphic output that Minitab has with this, and how it can be possibly an advantage to you. Again, it's kind of clunky trying to get it started out, especially in a virtual space. But once we get through the hiccups, we can get some really good detailed information. Okay. Sergio is wanting to confirm who is on what team. Jorge, Sergio, and Leanne, from what I understand, are going to team 4. Is that correct?
Yes.
Okay. All right. And so now, let me show you the pace that she's going to present these M&Ms. And this isn't the official start yet. Now, while you're actually doing this, what you can do is you can just write it down on a piece of paper, make yourself 3 columns, trial 1, trial 2, trial 3, and have yourself, 10 rows where you can collect information for yourself and then put it into the spreadsheet. And I think that'd be much easier than trying to go directly into entering into the spreadsheet. So put it down on a piece of paper first, and then, populate it into the spreadsheet. When you're putting it down on the piece of paper, you can just, give yourself a G and a B, all right? But just make sure that when you put it on the spreadsheet, you're spelling out good and bad. All right. So this is the pace that she's going to take you through. I just want you to see, how you're going to be evaluating this. And so, like I said, she's going to let you look inside the cup. She's going to spin the whole thing around. And what you should recognize is that you get ample time to judge and evaluate each M&M. Now, the way that a gauge R&R should be set up, as far as time is concerned, whether it's a attribute study or whether it's a variable study. So we're doing the attribute study here. The time that's allowed for evaluating good or bad should really replicate what's going on in your real world. How much time is a person, spending to evaluate this M&M in the real world? This is, if it really was M&Ms that we was evaluating, this is probably way more time than a person would have in the real world. But for the purposes of this study, I want to make sure that you had a good opportunity to really evaluate. And so I like this example. All right, so that's the pace that you have. Now, before I get the official start, when did you have time to get your paper ready and all that kind of stuff? Give me a TU if you're ready to start the study. Give me a TU if you're ready to start. You want to watch the video directly? Okay, this is what I'm going to do. But I need you not to go beyond round 1. Okay, so after the first round, I'm going to share the video link so you can watch it directly. Just skip to about 40 seconds. So if you're watching it directly by yourself, skip to about 40 seconds. Don't go past round 1. Let me see where round 1 ends. Okay, don't go past 4 minutes and 30 seconds or wherever you've evaluated the 10th one. Stop there and say done. Type in done when you're finished if you're watching that independently. For others, if the camera is not freezing up on you, I'm going to go ahead and roll it here. I'll even give you the elevator music.
Music on and we'll get started. Okay, round 1. So here we go. All right, that's the end of round 1. I'm gonna put you guys on kind of hold, enjoy the music, and I'm gonna switch you up for round 2.
Okay, are you enjoying the music? All right.
Quick question, Robert. So we
Sure.
said we're rushing into, we're only doing round 1, correct?
Yeah, you should have the data collected on round 1 right now.
Okay, okay. Just making sure.
Okay, and Erica, did you finish?
Yes, I did.
Okay, give me a TD if anybody did not finish. If you're watching it independently and you did not finish, give me a TD. Okay, and so your team can decide, whether you're, appraiser 1, appraiser 2, or appraiser 3. Go ahead and put your round 1 information in. I see that's starting to populate. Now, whoever is appraiser 1 in team 4, make sure that you're starting with a capital letter on both bad and good. So change those to a capital letter for just starting the word out. Lainey, you said that you're still unable to edit? Okay, thank you.
Mr. Robert,
Yes.
I see that the test items, they're not in order from 1 through 10, so we have to match them and match the order, right?
No, the test item, that's my control of which item is in what sequence. Okay, you're just measuring, you're just putting in the sequence that you measured them. Okay, so it should just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for you.
Okay, so we disregard the test items order, and we just go.
Yeah, that's just our code to say, what item was presented. Like the first item that was presented was that green M&M, and that's item number 7. And then when you see in round 2, item number 7 will be the third M&M that's presented. Do you see what I'm saying?
Okay,
So,
yes. I think that was just a
yeah.
confusion.
Yeah.
Some people,
Yeah.
like in our
So
group, we were
your
talking.
sequence that you're putting down for your responses should be the same sequence that you saw the M&Ms in. And so whatever sequence it is on your piece of paper, that's the sequence that you'll put down here. I appreciate you bringing that up.
Thank you.
See how fun this gets, trying to do this type of an exercise in virtual space? But once we get to trial 2 and trial 3, it'll get easier as we go. Kristen, stay in your own backyard, man. I knew that was going to happen, Kim. See, if we were in the real world, doing this live in person, I do actually pass out bags of M&Ms, so people aren't tempted to eat them out of the cups. So everybody gets their own little bag of M&M. All right, we're almost through capturing data on this first phase. Is that a proximity allergy, or are you talking about just when you ingest it, Trinice? Oh, wow, that's a terrible affliction. I've been allergic to a few things in life. Sometimes it comes and it goes, but I've never been allergic to chocolate. Okay. All right. So now we have the data collected for the first round, and so we're going to get set up for the round 2. And again, if you're watching this independently, then just don't go beyond round 2. And like you did for the first round, capture this data on your own piece of paper first, and then the sequence that you place it in the spreadsheet should follow the same sequence that you're capturing it while you're watching it.
Back for round 2. Sorry, guys.
Environmental noise.
And last one. All right, there you go. I'm gonna put you guys on pause again. That's the end of round 2.
Okay, so that's the end of round 2. You should have 10 items listed. And again, you're going to follow the same sequence that you have them listed. You're going to put that down for your response in the spreadsheet for round 2. I see with a little bit of practice, we got some real go-getters now. I mean, that information is just flying on the sheet now. That's good stuff. Give that a minute. I want to make sure we're completely queued here.
We struggled and we struggled. I'm not gonna lie.
What's that?
I said we struggled and we weren't really sure like what to enter where.
Yeah, but you're doing good on the second round. First round, maybe it was a struggle. Second round, I think you're getting used to it. Good. Somebody filled in Kim's section. Team 1 appraiser 2. Somebody had a sequence of bad, bad, good. Let's see. Whoever the dinosaur is. We got a bad dinosaur. No M&Ms for the dinosaur. Okay, and you know, I'd say, Kim, there's a good chance that whoever that is team 2 appraiser 2, because they probably looked at the sample here and thought that that was the first one. So who is team 2 appraiser 2? Okay, and so so is this? Let's straighten this out right fast, Michelle. Is this your sequence? Bad, bad, good, 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 bad, good, bad.
Let me double check on that.
If that's your sequence, we can just copy and paste it into the other one.
Yes, I believe it is.
Okay. Yeah, and so that should straighten out your situation, Kim. Okay. Looks like all the teams have it. All right, we're going to go ahead and go into round 3.
Time for round 3. It's the last round. And last one. Okay, guys. That was the last round of our measurement system analysis M&M.
All right, so you should have 10 now, and so we can go ahead and start populating the sheet for the last time. It's going to be leading us right up to break. When we get back from break, what we'll do is we'll collect this data, and we will run the analysis one team at a time, and see what we came up with. Who is team 3, appraiser 3? Ro, your team 3, appraiser 3. Did somebody erase your last entry? There we go. All right, thanks, Ro. Thanks for the integrity. You know, you could have said, yeah, they keep messing with me, man. All right, and it looks like we have one more entry. Wherever my dinosaur is. Team 1, appraiser 2, your last entry. Maybe you have to hit enter on yours too. Who is team 1 appraiser 2? Okay, Kim, check your last entry. There we go. All right. So amazingly, we got through that exercise, and it has brought us up to a great time to take a break. Yes, applause to everyone, all right, because this is not easy, you know, to coordinate. If any of you ever saw that commercial herding cats, if you saw that commercial herding cats instead of herding cattle, herding cats, so we discuss you know, herding cats all the time in the United States Navy. I spent a lot of time herding cats in the Navy. Sometimes when we do an exercise like this in the virtual space, it can be like herding cats, but we got through it good. And so let's go ahead and take a break. When we come back from break, we will go ahead and get into analyzing. But tell me, is this a time we should take lunch, or should we go ahead and go one more session and then take lunch? You can go ahead and voice up. You want to take lunch one more? Okay, one more session. All right, good. I know that it helped the Arizona people too, because they're not even thinking about lunch yet. Yeah, I get it. All right. All right, and so yeah, we'll do one more session, and I'm going to give you a good break right now. So let's come back on the hour, and if you need to go find some M&Ms, go ahead and find some M&Ms. We'll get you some carrots or something for Nice, so don't worry, we're not going to threaten you with M&Ms. All right, good deal. All right, get something to munch on, and we'll come back at noon, or noon my time. We'll come back on the hour. All right, looks like we have most back. And so what we're going to do is we're going to go ahead and go into this example from Minitab. And so if you have Minitab, you can go into the assistant, go into measurement system analysis, and it's going to ask you, you know, follow this decision tree. And so what data type do we have? Well, we have an appraisal as opposed to a measurement. So this would be for our variable data, gauge R&R, and this is for our appraisal. Now, you can set up the study, and this is where you would put in your gold standard and allow it to randomize the sequencing between trials. So you're going to tell it how many trials you're going to have, and how many appraisers you're going to have, how many parts you're going to have that are being evaluated, and then, you know, it'll randomize it for you. Well, we already had that randomized on the spreadsheet, so we can go straight into analyze the data, because the data that you had on that spreadsheet, I went ahead and copied it out of Excel and just pasted it here. And so we tell it to go straight to that analyze. Now, it's going to give you the columns that you have. It's going to give you the column headers that you have. When I set up an attribute agreement analysis, or if I'm doing the variable agreement analysis, then what we're going to do is we'd like to have our column headings match basically what is going to be asking us here for. So that's why I use the title appraiser and trials and test name and stuff like that. So it's very intuitive when we get to this screen. Now, the only thing that I'm going to need to vary here is the appraisal results section. So it's going to want me to know, do I want the appraisal results from team 1, team 2, team 3, or team 4? And it has to know what you're saying are the standards. Now, the spreadsheet that you saw in the first tab, I didn't have the listing of what the standard was because I didn't want to bias you. But in that same spreadsheet, if you wanted to toggle over, you'd see the next tab shows what that gold standard is. And so this standard is what you're being judged against, basically. Do you agree with the standard? But you're also being evaluated. Did you agree with yourself and did you agree with others? And so here we got it selected for results team 2 to start off with. I want to show you what happens if I take this out of here and I go to results team 1 and hit select. It tells me more than 2 distinct values are in the columns. And so when you have something like that that shows up, what you have to do is go back through that column of information and you'll see appraiser 3. I'm not unmasking the name. Appraiser 3 kind of set us up for failure here because on this 88th line item, appraiser 3 said back as opposed to putting bad in there. And so the system isn't going to overcome that data entry problem. And so now maybe that's the only one in that line item. So we have to go back in, go to analyze, and tell it, you know, hey, we want to see team 1 again. All right. So trials, test items, and here we want to go to see team 1 and see if we corrected it that time. And it wants to know what is a good or acceptable item. Now we want to select good for good item. We could have had this keyed to where it said PF for pass fail, or we could have spelt out pass fail. Whatever we have spelt out in the rows is what it's going to detect here, but you can only have 2 things in the rows or else it'll give you the fault that we just received. Okay, and so now it says, okay, well, what it sees in the column is good and bad, so that's what it allows you in the drop down. But every one of them have to match. It's case sensitive, and obviously we can't call a bad a back. All right, so now we have the results for team 1. Now, when you're using Minitab, you can grab the bar up here and slide it down, or you can tell it that you want to view the output only. Okay, and it'll give you larger real estate to view. Now, where we're at is we have an overall agreement of 64.4%. It's telling you that this is towards the no decision, that you can't trust this measurement system that's in place right now because, you know, I've fallen far beneath where we want to be. We want to be no more than 80% variation and definitely no more than 70. But realistically, we want to be more in this green, this color green shade or this one right here. So this is the 80 region and this is the 90 region. That's where we really want to be. So what happened here? Well, again, I'm not unmasking names right now, but our overall error rate is 35.6%. And we have good rated bad at 18.5%, bad rated good at 42.9%. And here's a big thing right here. Mixed ratings, the same item rated both ways, 46.7%. And so where are those differences coming from? Well, we can look, and this gives us a report card, and it tells us the exact item number. Okay, so item number 1, item number 9, item number 3 were percent good rated bad. Okay, but when you look at this percent bad rated good, item number 2, 5, 4, these have huge percentages. And when you see a huge percentage like this, like 100%, 100% of the people that evaluated item number 2, it was bad, but they rated it good. And so that tells me maybe my gold standard is wrong. You know, when I see something like 100%, maybe my gold standard is wrong. So maybe I need to go look at item number 2 and verify that I didn't miskey the gold standard. But there could be something else. It could be an absence of training. You know, everybody, there's a systemic problem. It's not just an individual problem. There's a systemic problem here with item number 2. And I know that because of the very high percentage here. I'm also suspect of item number 5 and number 4. And so I want to go investigate the gold standard finding on those particular items especially. And then, you know, maybe this amount of variation, maybe that's just a training deficiency type of a thing. Now, when we look at the individual appraisers, appraiser 1, appraiser 2, appraiser 3, appraiser 1 was significantly guilty of rating things both ways. Okay, so between the 3 trials, appraiser 1 rated things both ways in an excessive manner, far over 50%. And so a lot of our problem with this entire measurement system may be solved by helping appraiser 1, you know, distinguish between those good and bad. Now, appraiser 3 did quite a bit of rating both ways also. Appraiser 2 did pretty good. You know, this is pretty good not rating it both ways. So again, we can get very specific. It was good rated bad, so we know, you know, what percentage of time. Okay, but this percent of bad rated good. Okay, so there were bad items per the standard that were rated good a lot of times, and so we want to focus our training on making sure that people really understand what is bad. Okay, so this is just team 1 results, and then we can go back to the view where we see data and output, or we can go to data only. It doesn't matter. And then we go to measurement system analysis again. We tell it to analyze data, and then we would need to pick up another team here. So once you run this test once, it'll keep all these things the same. And so if you just want to switch out the team, you know, it makes it pretty quick and easy, but it will make you select, you know, what is good again. Okay, and team 2, incredibly, has actually done worse. All right, not picking on team 2, all right, but look at our percent of good rated bad and our percent of bad rated good. And again, we see these items, you know, item number 4 and item number 1. And so, you know, is that the same item numbers that we had before? Okay, well, all we got to do is look there. See, item number 2 was the big issue here. And now with this other team, item number 4 is the big issue. Item 2 is still of concern, but it's not the biggest issue. And so what is that starting to tell you? Well, you know, there's not consistency in the errors between these teams. And so is it systemic? Is it the gold standard, or is it training? We can pick up more evidence by checking additional teams. And so now we'll go into measurement system analysis again and pick up team number 3. And so here we want to go to this results, pick up team number 3, select, say it's good. Team number 3, pretty common. Okay. Item number 2 is the top dog now, and item number 5. 2 and 5 are the top dog. 4 is still a consistent problem, but you see in some rotation here as to what is the greatest concern. And so, and then again, you get to look at the individual appraisers, see which ones were really ranking them both ways. Okay, in this situation, it was appraiser 3. So all we got to do is vote appraiser 3 off the island, and this team would be doing a lot better. I know you guys think I'm picking on you. I'm not picking on you. All right, let's see here. That was 3, so let's look at 4 real quick. Good. Look at 4. Team 4 wins. All right, you're at 76.7%. You know, if you just just a tad bit more, we would actually say you're at 80% and you're good to go. You're really close. Team 1, Team 2, and Team 3 are matched here in their performance. Okay, and I don't know how in the world that happened. Okay, but they didn't find any that were good that they rated bad, and so this stays completely blank. And so the things that they said, they didn't have any miskeys, I should say, where it was a good and they rated it bad. They did have some bad that they rated good, and so let's figure out what's going on there. Now they had also some potential to rank both ways, but if you look at the scale down here, see the bar looks pretty long, but if you look at the scale down here, this goes up to 40%. Now you compare that to the scale on this previous one, this goes to 50% and beyond, and you compare that to this previous one, this goes up to 100%. Okay, so don't just look at the length of the bar, look at the scale down here on the bottom, and you can see that Team 4, the composite team, the composite team ended up being the best. Okay, so how did that happen? I don't know, maybe cross-pollination, maybe having some cross functionality on the team helped out. No, I'm just inserting that in there. Okay, this is a challenging test, to do in a virtual space. Again, I believe your results would have been much better had you have been live in person, trying to detect these differences in the video, even though she's going very slow, can be difficult. Okay, and so I give you credit for that, but give me a TU or a TD if you understand the tool and how it works and the advantages that it can bring you for being able to discern where some differences may be. And the whole idea with this is to give you a point of direction, not just say, hey, my measurement system is bad, but really to give you a direction to go to look to how to improve. Is it the measurement system as a whole? Is it the gauges that we're using, meaning the measuring devices? And much of that would be with the not the attribute, but the variable data. But is it the whole system that we're going to indict, or is it the tools that we're using, or is it the people? And if it's the people, which people and what aspects? Good versus bad, or bad versus good, or both ways. And so it can really be a good tool. It takes some time to set up and to execute well. But if you need to validate a measurement system where this type of analysis could come into play, then it can be very good. And you can do this actually with forms and documents and approvals and things of that nature. You just have to get kind of creative in your application and how you're putting things in front of people in a randomized way, to get their values, whether they think something is good or bad, or whether it should pass, or whether it should fail, or what have you. Just make sure that you're randomizing it in a good way, and they're not able to cheat the system. Had I have shown you the same sequence of M&Ms each time, you could have cheated the system. And so that's why we randomize the order. It makes it more difficult on the person that's setting up the study, but it definitely improves the value of your it improves the value of your analysis overall. All right, and so we covered a lot of material there in those videos and doing that exercise. There's a couple of things that I want to point out or stress. You know, when in the beginning of this phase, we said, you know, we're going to get kind of particular about how we use words, and it's especially important in any type of data analysis that when we're talking about precision, we recognize that that has to do with consistency of performance. And when we talk about accuracy, what we're talking about is correctness. All right, but there's a problem here, and it's a pretty significant problem, and it's probably all throughout your database analysis systems, especially in your dashboards and the way that you evaluate performance. A lot of organizations are just looking at the average performance and determining, you know, whether they're doing good or bad just based off of averages. And my concern is there's a lot of misinformation in just looking at averages. I'll give you an example. And so as you're looking at these targets, oh, hold on just a second. I need to switch your screens. Good thing I looked over at my screen to see that I didn't have you on track with the change there. Okay. Now you should be seeing a target now. All right, and so, you know, we're, like I say, a lot of your dashboards, you know, are focused on averages. A lot of your decisions that you're making as an individual, as an organization, you know, is based on averages of data. But I need to know more than just the average. I need to know the average, and I need to know the spread of the data. And so using these words, precise and accurate, you know, let's break this down with some imagery here. The first target, if we would say, hey, we're going to the shooting range and we're going to shoot at this target and the intent is to get directly in the center of the bullseye, then it could be easy to see that, that this first pattern of shooting is both accurate and precise, okay? But now what's inaccurate is the patterns that you see here, whether we're talking about an individual pattern or whether we're talking about, you know, 3 different individuals shot 3 different patterns here. So you got this pattern, you got this pattern, you got this pattern, all right? And either way, we can say that this is inaccurate, okay? But either one of these performers looking in isolation, we could say that they have precision. And why can we say that it's precise? Why would we say that that's precise? There, did that help out, Kristen? Kristen, I'm just wanting you to see this image here right now.
Yes,
okay?
I didn't realize that. That's fine, thank you.
Okay, that's fine. I'll shrink it when we're through looking at this image. But you know, so how can we say that it's precise? How are these shot patterns precise? Not a lot of variance where they're shooting, right? Absolutely, Trinice. And so what we're talking about is we have a very tight cluster here. And so what that means is, you know, this yellow performer, this black performer, this blue performer, each one of these individual groups are very repeatable in their performance, okay? Now, between them, there's a lot of variation, okay? But within their group, their performance is repeatable. It just happens to not be reproducible across many, all right? If say we disregard this shot pattern, that shot pattern, and we look at just the one cluster here, and this was representative of multiple people shooting that gun, then we would say that that they're repeatable within their own performance and they're reproducible against, you know, however 2, 3, 4 people that are shooting towards this pattern. Okay, but here's where it gets tricky. Down here in the lower left, we're saying that this is accurate, but it's not precise. Now, not being precise is pretty understandable because there's a lot of variation. It's not a tight cluster. There's a lot of variation in each individual shot, but we're saying that it's accurate. Now, how can we say that it's accurate?
Because the center of the target is what you're looking to hit, so it's closer to your goal.
Right, and if I looked at the distance away from the pinpoint center for each one of these shots, and if I consider it from like a vector location, you know, and I said, you know, okay, well, you know, from the center, this is this far, this far, this far, this far, this far, what I would get is I would get like this bell curve, and guess where my average would be between all those shots? Pretty much right towards the middle. And if I was looking at the reported average of distance from the exact pinpoint center between this pattern and this pattern, the difference would probably be undiscernible, okay, or pretty close to undiscernible. In other words, the average would look pretty much the same, okay? Well, that's big trouble for us. That's big trouble for us in our systems. Because if we're looking at a dashboard or we're looking at data analysis and we're just looking at the average, we're not taking into consideration the spread of the data or the shape of the distribution, well, then that's a big problem. And that's where that type of analysis can end up becoming misleading. Okay, so again, I want to look not only at the average, but I want to look at the shape of the data. You know, how does it appear to be, and the distribution. So you know, what we're talking about is the dispersion. What is the range of the data? What is the standard deviation or the variance of the data? We need to know these type of values, so we know how much variation is amongst all of the data. And a lot of misinformation can come from analysis of just trusting the mean. Remember, if your data is very skewed, the mean is not really going to be your central tendency because of things that can, you know, I could have this pattern right here that looks very good, very tight and everything else, but guess what? I could have one shot that's way off center, and that one shot, if you know it's a pretty small data group, that one shot that's way off center can throw that average way off. It just means that I'm very skewed because of that 1 or 2 shots, and so it's pulling my mean way over to the side. But where's the majority of it happening? The majority of it's happening right here, and so I need to. Maybe this is my common cause variation that's happening in here, and then there was some kind of special cause variation that happened here, like a person that was at the gun range and somebody bumped into their shoulder right when they were trying to shoot. Okay, so we can go investigate what happened with that data element, and we can figure out, you know, what was the special cause associated with that. And moving forward, we can try to prevent that special cause from happening again. But that's where we're going to start talking about, you know, the difference between common cause variation and special cause variation. If I have a data element or a couple of data elements that are far outside of the rest of my data elements, that's what I want to start doing. I want to start, you know, going to investigate. All right, but again, precision and accuracy. Sometimes we use this as being synonymous in terms and different types of language that we're using, but for the purposes of data analysis, we need to recognize that these are two very different things. What we just covered for bias, linearity, and stability with the gauge R&R, you know, that should be pretty easy to understand. And so that was pretty well covered in the gauge R&R section. If I have an expected average and then I have an observed average, you know, this expected, say it's more than just expected, that's the gold standard. That's what I know it to be. But this is what I'm finding it or reporting it to be, then that would be my bias or my inaccuracy. And so, you know, we got to figure out, you know, is our bias, what is the driver of that bias? And, you know, stability, if I have this exact package and I weigh it at one time and then I weigh it at another time and it's weighing out being different, then there's something in my measurement system that's not stable. Maybe it's a measuring device itself. Maybe it's the way that I place it on the scale. Maybe, you know, I didn't get it fully onto the scale or something else. And so we would have to find out, you know, what in my measurement system doesn't have stability, or what is the bias? What's the degree of bias? Is it linear? Does it stay the same across an operating range, or is it non-linear? Does it tend to change? And I don't want to go back into the gauge R&R studies because I think we've covered that well enough. I will tell you this. When we talk about measurement resolution, we're talking about gauge sensitivity. If we were doing variable type data as opposed to the attribute type data that we was doing, if you're measuring something of physical dimension, whatever your measuring device is, like say we got this ruler here, and I want to report within centimeters, I need to have at least 1/10 of a centimeter marked out here in my measuring device, and that gives me the proper degree of resolution and sensitivity. If I had a measuring device and I was measuring in units of centimeters and I didn't have at least 10 lines of demarcation between 0 and 1 and 1 and 2, then I don't have enough resolution or sensitivity. That's all that's telling you. That is a test question. All these things that I tell you are a test question. It's abundantly clear. It's pointed out in your material, and so there's nothing that, you know, will be on your test that isn't represented in the material. And so I told you while you was watching that video that ANOVA is considered the best method for analyzing gauge R&R studies, okay, as opposed to range and average method. Now, historically, when we used to do this all by manual calculation, or, you know, we were using Excel native, doing the ANOVA analysis, you know, it could take a lot more time. And so, you know, people were, you know, having to invest more time into it, and that could be a pain in the butt. But now it's like you push a button, you know, and you can get both the range and average and the ANOVA at the same time. There's no additional work to be done nowadays. And so really there's no downside to looking at the ANOVA analysis. All right, some potential interpretations, you know, when you're looking at the reproducibility area or reproducibility error or repeatability error, I just want to stress again, repeatability error would be the error within your own performance. In other words, trial 1, trial 2, trial 3, you don't agree with yourself. That's repeatability error. Reproducibility error is when appraiser 1, appraiser 2, appraiser 3 don't agree with them, you know, don't agree between the appraisers. And you can follow this mapping to figure out, you know, what you need to investigate when the operators may not be adequately trained, or when, you know, the gauge needs to have maintenance, or when there's ambiguity in the SOPs, things of that nature. But really, what's going to happen in the real world is when you use these gauge R&Rs, you're just going to have to go find out, you know, what do you need to investigate or study. And with the example that I provided to you that I think is going to be most useful to you in your organization is going to be the attribute study. I think that's going to be most useful to you in your organization. So I didn't spend a lot of time with the other example. If you would like, email me if you believe that you need to know about, you know, measuring the length of things or measuring the circumference of things, you know, and you need some support videos for that. I will be more than happy to send those to you. But I don't want to conflate this with information you don't really need at the moment. All right, so right now we're about to get into the review of the videos that you watch. Now I need a TU or a TD. Those that did not have time to watch it all earlier, have you had time to watch it yet? Give me a TU or a TD. Have you finished all 3 videos, CP, CPK? Bueller? We'll do during lunch, okay? So there's still a couple of people, I guess, that need to clean up on that. We will be going to lunch here pretty soon, and so you will have the opportunity to watch that. It's going to be very helpful moving forward. There's only a few more slides in this section, but they are a lot more relatable once you finish all 3 of those videos. But I will talk around the video content for just a minute. Let's just talk about what am I really trying to do with this process capability analysis without getting into all the meat and potatoes, okay? What I want to know is if my lower spec limit and upper spec limit and lower control limit and upper control limit, you know, is my performance fitting within my specification limits? Now, the lower control limit and upper control limit, these are known as natural process limits. This is what is within statistical process control. And so statistical process control is based off of 3 standard deviation below the mean and 3 standard deviation above the mean. That's not 6 standard deviations of performance, so it doesn't equate to 6 sigma level of performance. That would equate to a 3 sigma level of performance, okay? But it's being within this plus or minus 3 standard deviations that the rule sets, not that Bob created them, but Walter Shewhart, who developed statistical process control back in the 1920s and 1930s, working for both Southwestern Bell and Western Electric, okay, 2 very, very large companies back in the day in the 1920s and 1930s. There was no competition really to electricity distribution and phone service. They were the only ones on the block, booming, and you got Walter Shewhart is sitting here doing all the statistical process control development as a methodology for the first time in industries. And so he created this rule, and it makes sense, okay? 3 standard deviation above and below the mean being the threshold of what is considered statistically within control. And again, one thing that's very important to point out here is there's a big difference between being statistically in control and actually meeting the performance level that you want to meet, ideally, okay? And so we'll look at a couple of these pictures of cars and garages, all right? As you look at this car, how it fits into its garage, you'll see that there's not a whole lot of spare space there, okay? I would say that it's beyond a CPK value of, a CP value, I should say, of 1.0, which would be 3 standard deviation above and below the mean, because I do have a little bit of wiggle room here, okay? But if this was a situation where my one sport mirror on the right-hand side and my sport mirror on the left-hand side was basically touching or just about to touch the edge of each side of this garage, that's what we would relate to a CP value of 1.0, okay? And so what does that mean? Well, at a CP value of 1.0, what that means is, can you fit the car in the garage? Yes, you can, but there's absolutely no safety net. You have no insurance policy, okay? And what does that mean? That means if you get ever so slightly off center in your performance, if you shift and drift just a little bit, you're going to have defect, okay? And so, you know, what would we like? Well, what we would like is to have all this insurance policy that you see on the sides here of this vehicle, how it fits into its garage, right? Okay, there's no big crowding there. And so say if this driver was a little bit off center in their performance, is there an immediate threat of defect there? What do you think? No, okay. And this would be like a CP value, you know, probably of about 1 point. It's in fact, it's more than one. I would say this is probably about close to a 2.0. Okay. Why? Because I think that we could reasonably fit 2 vehicles of the same size within this space. Now, there may be some things in the background here that I need to be worried about, okay? But fitting through the door, yeah, I'd say we could fit 2 vehicles through there and still have room. But remember that difference between CP and CPK is that I could have this 3 or 4 car garage here. I don't know if this one's a 3 or 4 car, but if I'm way off center, then I still have the opportunity to have a defect because I'm way off center. I have this entitlement to all this space right here, but for whatever reason, maybe it's because we're going to park multiple vehicles in here. Okay, that's the situation. But for whatever reason, I'm way over here to the side. Well, okay, I have this potential, a CP potential. It's designed for a lot of accommodation, but in the way that I'm performing and parking this vehicle, I parked way up close to an upper specification limit or a lower specification limit. That's all that it's telling you. So when we start talking about reviewing these videos after break, you know, just think about this car in the garage analogy, and I think that starts to help you out. Now, what we want is we want the natural process limits, the statistical process control limits, to be within the specification limits, okay? Because statistical process control, again, is a CP value of 1.0. And so if my natural process limits are falling outside of my specification limits, then I have problems. Now, the way that I have this coded, if natural process limits were red and specification limits were green, my question to you is, are these images good? Are we doing well here? In either one of these images, are we doing good? So that's my natural process limit, red. and here's my specification limit, green. Is that good? Sergio says no. Jerry says no. And why not? It's not good because this red is the width of my vehicle, and this green is the width of the opening in my garage, and I'm trying to park this vehicle into this little garage. Or worse yet, I'm trying to parallel park my vehicle into a garage that won't accommodate that, all right? And so what we're looking for is just the opposite relationship, okay? And what we're looking for is my specification limits to be outside of that statistical process control or that natural process limit. So if I get some shift and drift, then we'll still be okay. Now in this situation, even without shift and drift, I'm not okay, and I'm not okay, and I'm not okay. All right, so when we get back from lunch, we'll get into the review of the videos. And because I know some of you need to clean up that video time a little bit, what I'm gonna do is give 45 minutes, so we'll come back at 30 minutes after. My intent is to get you out of here early today, but you got 45 minutes for lunch, and if you did not finish these videos, go ahead and finish these videos. Any questions before we leave?
No questions.
No? All right, let's come back at 30 minutes after. Okay, there's 2 more to join, but I'm going to go ahead and get started. What you had assigned to you for videos was the 3 videos on CP and CPK, and hopefully in viewing those videos, if it's been a while since you've worked with CP and CPK before, or if you've just never been exposed to it, hopefully these videos gave you a really good foundation that we can start building off of. And we're going to just have some high-level discussion about what you was looking at in these videos. In the first video, it just started, giving you the basics about, what percent of the data, falls under the curve at different sigma levels of performance. And so, as was expressed in the first video, at 6 sigma level of performance, a 6 standard deviation above and below the mean, before you hit a spec limit or lower control limit, upper control limit, spec limit, whichever you're applying that to, it gives you 99.9999998% of the data is going to fall under the curve. So that means 2 in a billion are going to fall outside of the curve or be in the defect region, or 1 in 500 million. And so that kind of is different from what we talked about before. At 6 sigma level of performance, we expect 3.14 defects per million opportunities. And so so what is that disparity? And that disparity is explained when you get to the second video, and it says, okay, well, that 2 defects per billion opportunity is what we would call a design or a short-term capability. But when operating in the real world, what we expect is if this bar here in the middle was our target objective for the mean, and then this bar here represents the mean as it actually shifts across time. And this is our expectation. We're going to see some natural shift and drift of that mean. You may see what we call, just a regular breathing pattern of the standard deviation. And what that means is maybe my bell curve, looks kind of slim here at one point, but then at another data collection point, it's breathed a little bit, and I get a little more variation, across time, and then it'll come back in, and it'll be slimmer, and then it'll be fatter, and then it'll be slimmer, and then it'll be fatter. And so that's just a breathing pattern, of that variation. And all that can still be attributed to common cause variation to a certain degree. And it's when we exceed certain boundaries that we start suspecting a special cause variation. But if my target objective is to keep the mean at a centered location between my upper spec limit and lower spec limit, then I need to know when I'm shifting and drifting away from that. Because as we expressed with CPK in both the second and the third videos, what tends to happen is as I shift and drift, or what will happen is as I shift and drift away from that mean, I have an entitlement here with this situation to have a CP value of 2.0. So that means, I have a quality level that's equivalent to a 6 sigma level of quality. But because I've shifted towards that upper limit, then when you do the math, you're going to find out, oh, well, my actual performance is much less from a CPK perspective. I'm no longer at 2.0. And I can't remember what this one got to. It's not reflected down here, I don't think, but it's, just above 1 is what I ended up with. And so this because I shifted too far away from that mean. And so in this situation, my car has moved too close to the to one of the boundaries of the garage wall. And so in looking at these videos, hopefully what you picked up was a couple of storylines. One is, if we were looking at the data graphically, the difference between a 2 standard deviation, 3, 4, 5, and 6, you should see graphically, a dramatic difference in between here. But where the difference becomes really important is not just what my short-term capability is, but how am I performing across the long term? And, are you seeing some shift and drift? And then the first 2 videos really are focusing on one dependent situation, the temperature of the coffee. When we get into the third video, we start looking at the effects of that row throughput yield. We start looking at the effects of interdependencies. And so, being at a performance level of 0.9975, well, that's all well and great in isolation. But if I have that performance level multiplied times itself, it starts dipping down. 2 interdependencies, not a big deal, okay? But as my interdependencies increase and the complexity of whatever system that you're evaluating increases, that's where you start seeing the dramatic impact. And so in this situation, there was 100 interdependencies, a quality level that starts out very high in isolation, gets to 78% row throughput yield, or first pass yield, by the time that it gets through all of these interdependencies. And so the only reason why we're at 78% is because we started relatively high in the first place. What I asked you to think about yesterday was if you was at a level of 95% capability, and you'll notice here that if I was 95% capable, that means 2 standard deviation as opposed to 3 or 4 standard deviation. If I was 2 standard deviation above and below the mean, and my performance value If I raise that to the 7th power, 0.95 raised to the 7th power, that puts me at 69% row throughput yield, defect free. So what does that mean? It means I have 30% defects. And this is a level of a cost of poor quality that you're not going to be able to absorb well. And so by and large, we say 2 standard deviation above and below the mean is an inadequate performance level. Whether we're talking about the potential of shift and drift, or whether we're talking about the interdependencies, the bottom line is 2 sigma level of performance is garbage. And not just because Bob says so, but it's not even statistically within control. Remember, the threshold for statistical process control is you need to be operating with 3 standard deviation above and below the mean without defect, okay? And so that is a CP value of 1.0, and that gives you 3 standard deviation above and below the mean, being defect free. And then at that point, you're considered to be statistically within control, not necessarily the performance that you desire or that you need, but at least you're stable and you're statistically within control. So we can go into analyze phase and we can count on the validity of the hypothesis test and things like that that we're going to run. If you do a capability analysis with data and you find out that you're less than a CP or CPK value of 1.0, you find out that you're less than that, what it's telling you is you're not within statistical process control. You need to put the microscope on whatever that process is and find what is taking you out of that capability of control, clean that up. And a lot of times that's what we call the lean clean, and clean that activity up so we have reliable data to take into the analyze phase. Reliable data based on being within statistical control. Now, in this 3rd video, you also saw, hold on just a second, let's get past that.
Most homeowners insurance providers can give you a quote online, but you know what?
200 components above the final output stage. We need much higher quality level and even hope to have a half-decent.
All right, so in the 3rd video, you also had this concept being related to your transactional flow, administrative responsibilities, things like that. Excuse me. And I think that that's a good opportunity to think of it from that perspective, where we're talking about sub-processes of some administrative action or transactional action that we're completing in our process. And so you have 20 sub-processes that are feeding into a major process to get a final output. And again, if we were at a 0.9975 for each of the sub-processes
output or produces
in isolation, that sounds like a good quality level. But in reality, when I multiply that times the interdependencies, then what we find out is it's dipping down even just at 20 interdependencies, 20 handoffs, or 20 elements on a data spreadsheet. Okay, whatever the situation is, if each one of those data elements was only at 0.9975 reliability, by the time that I have 20 data elements, the overall output of whatever that data spreadsheet is producing is only 95% accurate. And so this, again, the point that we're trying to make here is not just about making widgets in a factory. It very much applies to your transactional flow processes as well. And he gives an example in the video about, if you was typing 400 words, how many errors would you have in that? And he says, last time that you was typing 400 words, are you telling me that you didn't get those little squiggly lines underneath one of your words, meaning that you misspelled one of the words? Okay. How many of you have been typing something before and you get those little red squiggly lines saying that you misspelled something. Give me a TU if you know what I'm talking about. Okay. So it looks like most people at some point have misspelled something. Okay. Now here's the thing. As long as your system that you're operating in gives you that immediate detection, and you have the discipline as a person that's typing something to stop and correct that in place before you pass it on and send it to somebody else, we've minimized the damage of that error. Hopefully that makes sense to you. Okay, and so this is one of the ways, besides redundancy, besides, you know, everything that I type being sent to Michelle and Michelle has to review it and improve it, that would be redundancy in the system. You know, chances are, if we're just relying on Michelle's eyeballs, just like we're relying on my eyeballs, and I don't have something embedded into the system for error detection, then Michelle is probably going to miss it too. Why? Why? Because, you know, Michelle is just as impaired as I am? No, that's not the point. The point is, you know, what are we asking human beings to do? And how much attention to detail do you think that we're going to get out of one person? I asked you to count the number of basketball passes, and we couldn't come into agreement on the number of basketball passes just within 30 seconds. And so if we're looking at 400 words being typewritten, and Michelle not only has to look at my work, but she has to look at 10 other subordinates' work, you know, the chances are, even if Michelle is a PhD and a grammar smith and everything else, it doesn't matter. What we need is we need something in the system that's capable of identifying when a defect or an error, and then alerting, and then we need the cultural response and the behaviors at the operator level to where we're going to regard that and we're going to take care of it. Does that make sense to you? All right. Michelle, tell me, have you ever ordered something online from any online store, Amazon or what have you? Have you ever ordered something online and it doesn't let you complete the ordering process because you filled in one of the blanks wrong? Yes, and I think we've all experienced that, okay? What do you have in your forms and documentation and your administrative procedures, whether it's intake from the customer base or whether it's workers in your process flows? If we have an error, if we have a process or a form or something that tends to have a lot of errors, what do you have in your system for mistake proofing? So when we get into analyze and improve, we're really going to put that under a microscope and start analyzing, you know, well, how are we staging people for success? And are we doing it well enough? And are we doing it across the board? Do we just have isolated, you know, programs and processes that are protected that way, where we have problem statements and where we start investigating for, you know, what is my error rate and where are my susceptibilities? You know, those are the type of things that we need to start taking in to analyze and improve. We can start detecting it in the measure phase. We'll start to detect it in the measure phase, but now once we've detected it and we know that there's some issue, those are the things that we take in to analyze and improve. Okay, so not everything is about a cup of coffee, unfortunately. So, you know, if it was just as simple as a cup of coffee, I think we could all get to a state of perfection across time. But, you know, realistically, it's about whatever your situation is. And a lot of times with your organization is going to be things that are in the transactional flow environment. So we need to take the cues that this investigation about CP and CPK, really it applies to whatever performance level you want to put under that microscope. And when we talk about the difference between this short term and this long term, in the short term, you know, maybe my range of performance is completely centered, but as I start to get that shift and drift, my entitlement, what I'm designed for, may still be at a CP value of 2.0. A CP value of 2.0 equates to a 6 sigma level of performance. Okay, but my CPK starts getting deprived as at 3 standard deviation above the mean. As that starts to touch my upper spec limit or my lower spec limit, that score will be exactly a 1.0. A CPK value would be exactly 0 as my mean of whatever sample group I'm evaluating actually is completely on the upper spec limit or the lower spec limit. When it's somewhere in between, you know, it'd be a value between 1.0 and 0. And so as I start to go, as my mean goes beyond the upper spec limit or the lower spec limit with my sample group data, that's where I can get into the negative numbers. So I'll get like when 3 standard deviation away from the mean is exactly touching one of these boundaries, that's when I'm exactly a negative 1.0. So hopefully you see this relationship between CP, CPK as it's stressed in the video. Your CPK will never be greater than your CP. Your CP establishes what is your design capability and what is your entitlement. And if you don't like that, then you have to improve something there. But then the CPK is really, it's a measure of how well are you centered between this upper spec limit and lower spec limit. Okay, so let me see here. All right. So where we're going to take this process capability study, you know, what we're going to most acutely focus on is those things that we started isolating out to be the critical to qualities, the CTXs, critical to on-time delivery, critical to the temperature of coffee, critical to cost, critical to safety. Whatever those CTXs are that we want to have under evaluation, that's where we're going to put this amount of effort or this degree of effort to see what is our process capability level. And then we also need to make sure that we're paying attention to the voice of the customer, voice of the business, and regulatory or industry standards as far as what we establish as what are those spec limits. You know, your spec limits truly should be determined and decided by the customer requirements. Now, the voice of the business or regulatory standards may even cause you to say, okay, well, the customer only wants this for a spec limit, okay? But guess what? Because of the voice of the business or because of industry standards, you may even have to get more restrictive than that. And so whether we're talking about an on-time delivery or whether we're talking about the number of errors or defects, you know, on a form or what have you, it's, you know, we got to set those spec limits by the most stringent criteria, whether it's by the customer want, needs, or desires, or by the voice of the business, you know, or by the regulatory requirements. So it's whichever one of those requirements are most stringent. As we go into analyze, we need to start sorting out the difference between defects and defectives. A defect, say I have this ink pen here, okay? A defect could be a blemish in a logo, or maybe a little chip in the casing of the pen. But does the pen still write? Does it still perform the function that it was intended to perform? And so if it still writes and it still performs that function, it has a defect Now, whether the customer is willing to accept that defect or not, that's a matter of, you know, specifications from the customer. But this one pen could have 100 different defects with it and still be usable, or it may not be usable, okay? But it could have any number of defects. Now, if it's defective, then that means for whatever reason, either because of customer specifications, because of regulatory requirements, or because of the actual functionality of the pen, if it's defective, it's unusable for its intended purpose. And so as we progress forward, you know, and we start thinking about defects and defectives, that's the type of language that we're going to use. And we'll take that when we get into the control section, is really where we're going to start talking about control charting, and whether we're using a P chart or a C chart or a U chart, whether we're using a P chart or an MP chart and things of that nature, you know, to do the control chart monitoring on defects and defectives. We'll get into all that language once we get into the control section. How many of you, give me a TU or a TD if you've used control charts, if you set them up, or if you've analyzed them, if you're using them in your current system. Let me know what your familiarity is with control charts. Trinice in the past, TD. Okay. Well, when we get into the control section of this module, really that's the biggest part of what we're going to talk about that's relevant to you as an audience. A lot of the content in the control section really is just kind of notional forms that you can use to control a project or control the decisions that are made for a reaction plan coming out of a project. But it's a lot of notional forms. So we'll look at those, you know, at just basically a very subjective level. But the interesting information is the control charts and how you set them up and why you would want to use them. And they're going to demonstrate, you know, 15, 20 different types of control charts. I'm not going to go through each one of those intimately with you. There'll be videos that are available for future viewing. What I'm going to show you is the ones that you are most likely to use and to benefit from. But beyond that, you know, as a precursor to that, we're just going to talk about control charts in general, why you need them, why you should be employing them, and what advantages, you know, that they can bring to you, and basically how they function. And then we'll get into some of the most common examples. All right, but as we was discussing earlier, when we're doing process capability studies, and really when we're doing everything that we're going to do in analyze phase, we need to start sorting out, you know, not just if we have variation, but specifically what type of variation that we have, whether it's common cause variation or whether it's special cause variation. And so again, that common cause variation is that natural process variation. It's that swaying of the skyscraper that is actually by design. We need to allow some freedom of movement, and we need to allow some level of variation within our process, or else we're going to break it, or we're going to spend way too much money on trying to get it completely stable without movement. It's cost prohibitive. You know, it's not a good investment. You know, after a certain point, you're not going to get that return on investment by trying to make something to where it has absolutely no variation at all. I don't know if somebody was trying to say something there or if that was just happenstance. Was somebody trying to speak? Okay, what we may have had there is just a little bit of special cause variation. And so what is a special cause variation? You know, it's some type of external factor. It's sporadic in nature. You know, it's not going to happen all the time. It's not by design. We don't consider it a part of the natural process variation. And these are the things that, one of the reasons why we run charts or control charts or other type of monitoring systems is so we can determine, where there is special cause variation, even as simple as doing the box and whisker plot. If I see something that pops out as an outlier to that whisker, I know that there's a potential of special cause variation there. And what is my concern? Well, my concern is that special cause is going to drag off the mean and make the reliance on the mean less reliable. But even if I get enough special cause variation elements coming in, it can have a more dramatic effect and impact even on the median. And so, the things that I'm trying to use to analyze my data and my performance can start giving me false signals. And of course, Erica says she's going to have to restart her computer. Okay, appreciate it, Erica. We're almost finished with this section, and so if I'm doing a run chart, and by the way, when we get into control charts, we're gonna cover how a run chart, we can go well beyond run charts, in sophistication level. And again, it's a matter of pushing a button, whether I select a run chart or whether I select a control chart. A control chart is going to tell me a lot more, so I'll use that as opposed to a run chart. But ultimately, what am I looking for? I'm looking for anomalies. I'm looking for trends or patterns, but especially with the special cause variation, I'm looking for an anomaly in my data. And we can do the same thing, with a control chart here. That makes better than a run chart is you're going to automatically get superimposed what is 1 standard deviation above your mean, 2 standard deviation, 3 standard deviation above your mean, and then the same for below it. And then it becomes very, very obvious if you have a data element or if you have a collection of data elements that are outside of that 3 standard deviation above or below the mean, then it's a point of investigation. Now, we're going to say that it's out of control as a point of investigation. In reality, what should I expect? I should expect 3 out of every 1,000 data elements are going to fall outside of what is statistically within control in these bounds, because I'm operating at 99.7% between 3 standard deviation above and below the mean. And so from statistical standpoint, I should expect 3 out of every 1,000 to be outside of that range. But as soon as I see 1 with just a few data elements down here, then that tells me from a ratio perspective, something may be off whack here. So we're going to go investigate what is that data point. And again, this will be a lot more clear once we get into control charting. You'll start to understand what these patterns are that we're going to look for and what other type of anomalies that we may be curious about or interested in investigating, even the things that are within that region. Now, the reality is there may be a particular reason why a pattern tends to develop in your data output, and that's fine, so long as it can be investigated, explained, and understood. But what do I expect out of natural and normal variation? I expect randomization. And so this illustration, gives you randomization. Here, we would call this cyclical. Now, there may be something in my system that causes it to be cyclical, but I need to go learn what's driving that cyclical pattern. And if this is just the way that process is going to perform and I don't need to be worried about it, then we'll learn that through our investigation. Same thing with trends, whether it's a decreasing trend or an increasing trend. If this tends to happen on a regular basis, that's fine. But see, what we get concerned about is if we got this decreasing or increasing trend and it's not something that we expect, well, what are we expecting for the data points going immediately beyond this? Either it's going to fall below or it's going to go above. And so we want to capture it early on and respond to it. But again, we'll talk more about these patterns and what we're looking for in your data when we get to control charts. Whatever you use them for your data systems and your monitoring techniques, whatever you're using currently in your dashboards or what you figure out, you know, doing the improvement project, whatever measures or monitoring techniques that you decide are necessary to add. A lot of times, what's important is that we have maybe multiple ways of looking at the same information, not to create redundancy, but to provide different angles of observation for the same type of data. But there's a tremendous amount of different tools and systems out there for monitoring and analyzing data. We'll cover some of these when we get into analyze. But what's important is that as a team, as you're doing the improvement project, if you find out that the monitoring system that you currently have, either there's something that needs to be monitored and it's not monitored, or your monitoring system is falling short of really giving the good intelligence and the good reaction plans that you need within the organization to truly control a process across time, then you need to maybe experiment with different types of monitoring programs. When you get into the analyze phase, you get into the improve and control phase, you can experiment, do some pilot testing within your system to figure out what's going to work best to give you adequate control over your process. So having said that, let's see, we're at 206 and we're wrapping up the measure phase. There'll be some topics that we step back into and pick up on as we go into analyze and improve. But by and large, that's where we're at with measure. So I'm opening the floor for questions on the measure phase. Floor is open.
Mr. Robert.
Yes.
I just wanted your thoughts on this. I know a lot of the statistical stuff or the calculations, it's something that might be maybe like in the manufacturing field be seen a little bit more. When it comes to like social services, I know, you know, statistics is still good to use, but in your opinion, or maybe I might not understand this correctly, but the statistics level or the threshold that we have to meet for social services, wouldn't this be just a tad bit more lenient rather than, you know, the harshness of, you know, having the Six Sigma when it comes to
yeah. You know, what level of quality you need to have for each individual process needs to be a focus point for your team to have a discussion on, and you know, it's a business case. Okay, what I'm going to tell you is, by and large, what I like to see is at least a 4 sigma level of capability across the board, and that gives you a CPK value of 1.33. So if on my CPK value, if I can maintain a 1.33 across time, then that's good, and that's probably a good place for you to be within your services. Now, where you may want to bump up to like a 5 sigma level of capability, which would be a 1.67 as opposed to a 1.33. Where you may want to bump up to that is those things that are most critical and gonna cause you the biggest problems, you know, with your customer base or regulatory requirements or what have you. But yeah, 6 sigma, 6 standard deviation above and below the mean without defect. That's far too much investment. It's too much insurance policy. It's that having that $20,000 vehicle and spending $1,000 a month on an insurance policy. Does that make sense? Okay, if you have a $20,000 vehicle, maybe you should be spending $100 a month on insurance. It's good?
Yes, sir. Thank you.
All right. Now, if the question is, you know, how much do these statistical methods apply to your transactional flow world? Very much so. You have to get kind of creative sometimes how you figure out that you're going to apply these statistical methods. But as we go into analyze, improve, and control, I think you're going to start to realize that. Time, remember, you know, I told you from the very beginning of the course that a lot of times what we're looking for is time. And everything that I'm seeing in your problem statements have to do with time. It's kind of strange, huh? All right. And so when we start to analyze things, or when we start to build control models for things, what type of data is time? What type of data is that?
Continuous.
It's continuous data. Okay, so all the things that we're about to go over and analyze that have to do with continuous data, normalized data, evaluation of data from, you know, the perspective of, you know, what is normalized and what is continuous data. Most of what we're going to discuss and analyze is going to have to do with normalized data. And if our data is non-normal and we expect it to be normal, then we need to go in there and find out what are the special cause variations that are driving that to be non-normal. But when I'm dealing with time, and when you're dealing with time, you know, your expectations of your data, you know, should be that it's going to normalize. Now, we're going to look at some non-normal data generators and ways to handle the non-normal, but I'm going to spend most of this time in analyze having to do with normalized data. And everything where you're trying to evaluate, measure time, and compare, you know, the time that it takes you to process something towards a standard, is that difference statistically relevant? Those are the type of discussions that we're about to get into. But before I get into those type of discussions, really, this is a convenient time to actually share first video that's kind of lighthearted in nature. I would call it a funny video. There is actually a good point here. And this video is going to take us right up to break time. Okay. Give me a TU if you've seen that 70s show before. TU. Okay. Got a TD from Leanne. All right. If you haven't seen that 70s show before, maybe you're not going to understand who these characters are. And one, you're not watched it either. It's actually a pretty good sitcom show. You may or may not be into sitcoms, but it's pretty funny. So just to explain, this is Michael Kelso. Now, one of his friends at the end of the video, as he does throughout the seasons, you know, typically refers to him just by his last name, so he calls him Kelso. But this is Michael Kelso. This is his father. Now, in this episode, it was career day, And so Michael's school assignment is to go to where one of his parents works. So he goes to where his father works, and he's supposed to find out what his father does for a living and observe that directly, and then give a report back to school on it. And so we're going to see segments throughout the whole episode, just kind of compressed together. And so, you know, in 3 minutes and 30 seconds, you know, we'll see various segments of this particular episode. Some of you may have actually seen the full episode.
So cool. My dad's office, dad's desk, dad's phone, ding ding. My dad. I love this.
Yeah, Michael, this is where all the magic happens.
Okay, let's get started. Question number 1. What's your job?
I'm a senior executive statistical analysis technician.
You're a senior executive what?
Well, in plain English, I concatenate diverse statistical information to maximize the potential utilization of data.
So, you give people data?
You know, a lot of people think that. No. My job's not about output, it's about throughput.
So, you throughput data?
Well, now you've lost me, son. Oh, listen, Michael, you know the 8 tracks you love so much?
You make them?
No. But because of us, other people who make them are able to make them better.
So you fix stuff?
You could say that, but I wouldn't. This is the performance index before my involvement, and this is after.
Okay. So you're responsible for this?
You can't credit me with that. That's probably a statistical anomaly.
But you made the chart, right?
I wish.
So do I. Hey. Do you have customers?
No, they're more like clients.
But you have clients.
Sort of.
And you provide them a product?
It's more like a service.
A service?
Well, not...
To maximize the potential utilization of the data.
If we did that, we'd go out of business. We look at the chi-squared here, apply the standard deviation here, and correlate the results with the actualization median here. And that's what I do. And I can't make it any clearer than that.
I'm just gonna say you're a farmer. It's time for the farmer.
At dawn, my dad and I were out in the field picking carrots fresh off the trees.
Kelso, carrots don't... That's good. You should put that down.
All right. So, do you like that video? Somebody voice up.
Yes.
Yeah, Jerry. I think that it's pretty funny. All right. And so yeah, I can definitely relate to Kelso too, you know, and so, you know, you say, Bob, well, what do you mean? Okay, well, you know what, if you haven't dug deep enough into statistics to find the part that you don't understand, then you haven't been digging enough. Okay. And, you know, to give you a case in point, you know, I was working with somebody brought up rocket scientist earlier, and I had some projects that did very, very well. One particular project was my payback project for my black belt certification in the Navy. To get your black belt, you had to do a payback project that was worth at least $1 million return on investment. And mine was valued at 37.4 and validated by 7 auditors from the GAO office. And so they said, oh, okay, you know, they elevated it up to the Secretary of the Navy. I got selected as one of the 10 best in the Navy, and it was outbriefed to Congress and all that kind of good stuff. All right, hoo-yah, good stuff. And then I'm at this Federal Improvement Symposium, you know, getting recognized. And then after I had the opportunity to be on a panel, I had this guy come up to me, and he's a rocket scientist, literally a rocket scientist. And he says, you know, hey, you know, Bob, you know, this may be outside of your expertise, but I really liked your project. I like your focus. He says, I got this problem with rocket fuel stabilization. And my algorithm, you know, I've been working on this for 6 months, and I can't, you know, fix the algorithm to stabilize this rocket fuel. And he was serious, by the way. And so he's looking to me to help him stabilize his rocket fuel by creating a new algorithm. And guess what? I was able to solve his problem in about 2 seconds. Okay. Does anybody want to guess how I solved his problem? Anybody want to guess? What's one of the options? What's one of the options on Who Wants to Be a Millionaire? One of the options when you get stuck is what? Phone a friend, right? And so the friend that I phoned was somebody that I had actually helped significantly with performance improvement projects in the past. And she just happened to be a senior executive SES level within the governmental system. She was a senior executive services officer for NASA, and her responsibility was everything on Earth that looks into space and everything in space that looks back on Earth. And she had 40 years of experience in NASA. And so my answer for him was to get her on the phone and let the two of them talk, and for her to put a team together for him from NASA to help him resolve this issue, because he was trying to do rocket fuel stabilization for the Navy, and the Navy and NASA have a tie point through SPAWAR, Space and Naval Warfare Systems Command. Okay, and so did I have to be the smartest person in the room to solve that rocket fuel algorithm stabilization problem? Did I have to know all the math and statistics for that? What do you think? No, it's all about resources, and you're absolutely correct, Erica. And so when you get to this wall, and you're hitting this wall and you don't have the answer, this is where we look to who can I turn to? What resource can I draw in? Can we build a team? I told you from day one, individually, I will fail. Individually, you will fail. But guess what? In the collective, we can be audacious and we can accomplish anything that we need to accomplish. Okay, and hopefully you understand that. And that's the reason why I'm sharing this story. I've had very successful projects in the past, but it's because of what we could do as a team, not because of what I could do as an individual. So hopefully that all makes sense to you. And so when we get to this point where we're talking about analyzed data, people are on different levels of the experience and the freshness of that experience. I'll say, you know, your recollection of those experiences. People are on different levels. I already know that from the pre-assessment, but I also know it from literally, I've had thousands of classes before, and I know, you know, that sounds like an exaggeration. Okay, you guys got to remember, I've been doing performance improvement since 1992. Okay, not always under the branding and the heading of Lean and Six Sigma, but it's always been continuous process improvement. And so, you know, this is 30 years of accumulation here. And so, you know, I understand. I really, really do. If you haven't failed at analyzing something from a data perspective, it's because you haven't been challenged enough yet. But when you get to that point where you're being challenged and you don't know what the answers are, this is where we seek out the resources to help us to grow and to learn and to recall and to understand. And so whether it's remembering something that you learned many years ago and you've forgotten, or whether you've never learned it at all, it doesn't matter so long as we work this as teams. And when you get to that point where you don't know where to turn, or you don't understand the tool or the method, or what an F-test is about, a t-test or a NOVA or a chi-square, that you go to where the resources are. I'm going to give you a lot of resources via video tutorials that I have embedded into this lesson plan, especially in this section. But beyond the video tutorials, go into those video authors and watching them, learning from them. But what's really going to be powerful for you is to find those people within your organization or within your circle of friends and professional contacts that can help you learn to do that. And so with all that said, really, what are we trying to do? We're trying to come from out of this very subjective root cause analysis, where we can sit around and brainstorm with a fishbone diagram and just have discussions about things, to actually going out and grabbing data and doing hypothesis tests with the data and letting the data help us to make decisions. And what slows people down from this is the uncomfortable nature of it, or is the unfamiliarity of it. And so what we're going to do here in this analyze phase of your instruction is not make you all statisticians. That's not my intent. We can't do that in 5 days. What I want to do is I want to give you enough exposure, enough confidence to where you can figure out what you don't know, so you can express what you need more practice or experience or more assistance with from the people in the world around you. All right, so as we start getting into this investigation of analyzing data, one of the big things that we're looking at, really, whether I'm talking about a control chart or whether I'm talking about a regression analysis, a lot of times what we're looking for is if I have an expectation of data to be in a certain location, what I'm doing is I'm measuring the distance or the error rate of where that data is from where my expectation was. And so that would be an example of like a linear regression. Well, we can take that information, that distance of where we find the data from where we expected it to be, and we can figure out, what are control limits around that. And so when we're doing residual analysis, whether you're doing all the math for it manually or you're just pushing a button, really that's what's starting to happen in the background. Now we're going to take this conversation into control charting, and you'll start to understand how control charts or certain control charts are developed in the first place. Okay, but this is really going to become apparent to us when we do get into regression analysis, because we're going to be able to predict where we expect this X to cause a data point, this value of X, to cause a data point to present itself somewhere on the Y-axis based off of the calculations that we're going to do for the regression analysis. And so we'll step into that, and it's going to be clear as mud by the time that we get through with this presentation. Right now, I just need you to understand that residual analysis is really in the background of a lot of the different types of tests that we're going to run. Okay, so at a very high level, just understand that what's going on in the background is It's finding out where data is located from a point where we expected it to be in the first place. Get into, okay, this discussion about data transformation. How many of you have used data transformation before, like a Box-Cox data transformation? Trinice, in the past, okay, and Trinice, by and large, I would like you to keep it in the past. and why might I say that, Trinice? What's the hazard of data transformation? What's going on with data transformation? I've got a lot, mostly thumbs down, and that's actually a good thing. I'm not a fan of data transformation unless you're a data scientist. And does somebody want to guess why I'm saying that? What does data transformation sound like? Change, okay? And like you're changing it. And see, here's the part that I don't like. It's like we're changing it from its original values into something else. And we're doing that with on a logarithmic scale and with exponential values. And so basically, why am I doing it? That becomes the question. Well, I may be doing it because my data looks kind of really like strange and it doesn't look normalized. Maybe it looks like that, or maybe it looks like this, you know, whatever. And I say, okay, I run a normality test on it, and I find out that it's not normal enough to do hypothesis tests that require normal data. And so if I wanted to do normal data hypothesis test and it's not normal enough, what a Box-Cox is going to do is it can take some exponential data, an exponential curve like this, and it can transform it and make it think that it looks like that. So then I can do hypothesis tests that require normal distribution of data, okay? This is junk if you don't know what you're doing and you don't know how to own the report out of the fact that you actually transform the data to normalize it. But then the big important part is understanding in your further analysis that this isn't really normal data, and the stuff that you're doing with normal hypothesis testing is now skewed, okay? There's reasons why data scientists use data transformation. That's why it exists in the first place. But if you're not a data scientist and you don't really know and understand what you're doing in this transformation or why you're doing it, then it's not good. What we do is we go to non-parametric testing equivalents to normal data testing, as opposed to trying to make a square peg fit into a round hole. And that's basically what you're doing with a data transformation. You're taking a square peg and you're trying to make it fit into a round hole. Again, if you're a data scientist and you know what you're doing, then that's fine. If you're not a data scientist and you don't know what you're doing, then don't do data transformation. Okay, let's see, was it Trinice? Trinice, have you ever seen somebody mess up on doing a data transformation? Come up with the wrong, pardon?
Yes, I used to work for NASA also.
Oh, okay, so you know exactly what I'm talking about. And again, if you know what you're doing with data transfer, oh, by the way, you used to work at NASA. So the SES that I'm talking about from NASA was Mary Esfandiari. Now, this was a timeline of about 2011, and Mary Esfandiari at that point had 40 years in NASA. Whether she's still there or not, I'm not sure. Okay, but yeah, that is cool, Trinice. I've worked a few projects directly with NASA. Wasn't with the rocket scientists though. When it's a rocket scientist approaching me, I pair them with somebody else. Why? Because we need somebody that knows what they're doing. All right, and so here's an example, of data that when I ran it through the original normal probability plot, it gave me this type of a presentation. Okay, so that's some type of exponential presentation. It's not fitting that normal probability plot. But then after I transform the data, then this is how it presents itself on a normal probability plot, and it makes it think that it's actually normal. Okay, but it's only making it think that. And if I can't account for the transformation impact that it's had, we just stay away from it completely. All right, so when we get back from break, what we're going to do is we're actually going to get into we'll talk about cause and effect matrix, but when we get back from break, what we're going to do is we're going to actually go into a couple of videos on hypothesis testing. And before we get too deep into the pond here, I want to make sure that we're all singing from the same sheet of music with regard to hypothesis testing, because as we go beyond just a simple cause and effect matrix that we've already seen a demonstration on video for, as we go beyond this, we're going to actually start getting into the hypothesis test. And I want to make sure we're all on the same sheet of music there. So we'll start with those videos. And I'm going to open the floor for questions before we take this break. Any questions? Okay, I have no questions. And so let's see. Let's come back in at 10 minutes till. And what we're going to do today is I'm going to be releasing you at 4 o'clock, but there's again a couple of videos that I'm going to want you to watch before morning. Does that sound fair? A release at 4 o'clock Central Daylight Time, but there will be a couple of videos. It won't be as long as yesterday's set of videos. All right. So let's go until 10 minutes till. All right, here we go. Okay, so where we're at is we left off on this discussion about process input, output variables, and we're looking at this configured as a C&E matrix right now because we use the same type of a matrix when we was talking about prioritization matrix, and now we just change what we're putting on the inputs and what we're putting on the outputs to represent input variables and output variables, and all of a sudden magically it has turned into a C&E matrix, and so you understand how this functions, so I don't really need to go over that too much more. If you want to give different weights to different output variables, you can do that just like what we was doing with the weighted prioritization matrix. Or if you want to keep it all with the same weight, and then you just don't put particular weights in there, and so you're just going to multiply times the the vertical and horizontal relationship and then add across, just like what you would with a prioritization matrix. So it functions very much the same way. So we don't really need to watch another video for that. What's important is when you do a C&E matrix, that you have a template for that. There's thousands of these type of templates that are available online. If your software package doesn't have this, you can have this with already having the formulas embedded into it, and that's going to give us the protection of any type of user error. You can Google a C&E matrix or a prioritization matrix or an XY matrix, under those different names, and you're going to come up with basically the same thing. I like, people using proven templates where we know that the formulas are all good, just so we don't induce an error in building up the matrix in the first place. But most of your statistical software packages, they're going to have this type of functionality already embedded in. And so if you're building it from scratch, you can come back and follow the step-by-step instructions, but I really like people to avoid building these things from scratch in Excel native anymore, just because of that opportunity. But ultimately, what we're trying to get to is a rank order of where we should prioritize our attention with the C&E matrix. It's going to tell us what cause and effect has the highest priorities, just like if you're doing this as a prioritization matrix, and then you can reorient that to where the highest numbers are going to populate up at the top. It would be the same type of effect that you're getting with a Pareto analysis screening tool. And so whether you're using Pareto analysis or whether you're using a C&E matrix, the bottom line is we need to start figuring out, what are we going to do cause and effect diagram on. Now we can do this traditional fishbone diagramming, and we can separate into the, traditional categories of manpower and material and methods and machinery. We can add measurement and environment, to give the full 6 categories. And then whatever labels or categories, your team comes up with that you feel is prudent, you can investigate towards whatever labels or categories you want, but these are the mainstays, the 6 mainstays. Now you notice this says maintenance is not a label, and I have that as a testable item because both ASQ and IASSC want to see if you'll jump on that. And we particularly don't put maintenance as one of the labels for a reason. And why do you think that might be? We got machinery, we got methods. Where should maintenance be? I may have, this may say methods, or it may say process, it may say procedures. Okay. Where do you think maintenance should be? Why do we say it's not its own label? Erica says maybe under machinery. This is what I want. I want the opportunity for maintenance to emerge both under machinery and under methods, because I need to maybe take some different paths there having to do with the maintenance of the machine or the method of the maintenance. Does that make sense? And again, it's not because Bob says so, it's because, those standardized tests and the body of knowledge, really wants to point that out. We want maintenance to be able to emerge in these different labels of traditional labeling. Go ahead and give me a TU or TD if you've used this root cause analysis, cause and effect diagram, Ishikawa fishbone diagram before. Okay. And for those of you that have that have used it before, which looks like just about everybody. There's a couple of pros here. One pro is we can get, people to readily understand what it is that they need to do. We can get a lot of active engagement if we execute it properly, make it large, put it on the wall. If your organization is looking for things like ISO validation, International Organization of Standards, ISO loves to see fishbone diagramming. Why? Because it's been around since the 1950s and is very well established and embraced in the quality circles. But I have some particular problems with it. And those of you that have used it before, maybe you have some problems with the fishbone diagram as far as it being a functional tool as well. Somebody express verbally what kind of roadblocks do you run into when you're doing fishbone diagramming? You got a problem here, you put it at the head of the fish, and now you're trying to ascertain what is the root cause, and you do this structure. What's the problem that you can run into? Several problems, and not one seemed to be more important than the other. Making use of, making sure you capture it all. Okay, Leanne, that's kind of along the track of where I'm trying to get to. This format gets so busy, so congested, so fast that it really is supposed to be a great visualization tool, but it can get so busy so fast. And then what are we really doing? We're just listing a bunch of things like, I'm going to list training. Okay, well, surprise, how often is training going to come up on manpower and methods? It's going to come up over and over and over again. Well, what is that really trying to tell me about training? And yeah, I can go into the 5 whys analysis. And so now as I take this out into 5 whys analysis, I'm asking why. Okay, and then guess what? And then I start asking that on skill and knowledge, and how busy is this going to get? It's going to get very busy. I lose the form, I lose the structure, I lose the conversation. And sometimes we just get the, whether we're doing this electronically or we're doing it large up on a wall, we just get a bunch of stuff plastered out there, and we say, okay, well, we've done enough, we've captured enough. And now what have you done? Really, you've just listed a bunch of problems, and you listed a bunch of different directions. Now, the fishbone diagram or any of this root cause analysis doesn't really mean anything at all until I start employing this 5 whys technique. And whether it's asking why 5 times, whether it's 3 times, whether it's 15 or 30 or 40 times, the matter is asking why enough to where you feel like you can gain control and you can establish some countermeasures, and you have enough control on each one of those line items to control the event. And so a root cause analysis, really, it's kind of mislabeled, because are you looking for the root cause, or is what you're really looking for what to do about it? Are you really looking for solutions? And what I would say is what you're really looking for is solutions. And so I like to convert the 5 whys. We go through the 5 why analysis, or 15 whys, or however many whys you feel like you need to ask. But then we need to turn that around and say how. If you're telling me that the why is training, and you need to implement new training, well, how are you going to implement that new training? And then you tell me, well, it's going to be these particular 3 items that you're going to do. Well, how are you going to do each one of those individual items, and how? until we feel like we have the full list of everything that we need to do, and we have parameters established that tells us now we have a robust solution. So one thing that I have about fishbone diagram is its format and its structure becomes very limiting. And so I'm not telling you not to do fishbone diagram. It's a great conversation starter, and it's something that people can feel familiar with or comfortable with because of familiarity. That's fine. Start the conversation out that way if need be. But I'd like to see you take something more robust into your root cause analysis and your search for solutions. And so how many of you have heard of the Apollo method or cause mapping before? Let me know if you've heard of the Apollo method or cause mapping. Okay. You're gonna, I think you're gonna like this this example of cause mapping as a alternative to or a supplement to what you're doing with the fishbone diagramming. And this cause mapping example, you know, comes to you from Think Reliability, and Think Reliability has a lot of cause mapping video tutorials out there that are based off of critical incidents, and such as this one. This particular example is the Exxon Valdez oil spill, and it's doing a cause mapping root cause analysis study on that. But they have it on like airplane crashes or explosions and things of that nature. And the reason why it tends to gravitate towards case studies being available for natural disasters or man-made disasters is because of the Freedom of Information Act and the international laws that are associated with disclosure of these type of investigations. And so this isn't private company information, even though it's about a private company. Once you have a man-made disaster or a natural disaster, there's a requirement for disclosure to the public, because it's the public that gets threatened by these type of situations. And so we have a right to know. And, you know, I'm giving all that information for a very specific reason, because the type of case studies that you'll find out there have to do with critical incidents. But in reality, cause mapping is very robust towards any type of process, any type of business problem, you know, whether you're in the transactional flow or the physical flow. It's just that you don't have all these companies and agencies and organizations that are going to be willing to put out their case studies off their cause mapping, because it's a lot of putting your dirty laundry out there to hang for people to see. And so if they're not forced to disclose, they're typically not going to share that information available in the public. All right, so having said all that, this is a very good video. If you have trouble hearing her, because it is a little bit soft-spoken, if you have trouble hearing her, let me know and I'll provide the link to you. So just, you know, voice up, you know, Bob, I can't hear it. If we can see it as a group, that would be my preference.
Valdez, a third mate is on duty.
Okay.
On May 24th, 1989, on the Valdez, a third mate is on duty past his shift and realizes the calculated position of the ship is off. He orders...
Are you able to hear that? Okay. Could you activate CC? Let me see if it has that option. Okay.
On May 24th, 1989, on the Valdez, a third mate is on duty past his shift and realizes the calculated position of the ship is off. He orders hard right rudder and calls the captain, but before anything can be done, he grounds off Bligh Reef. A total of 10.8 million gallons of oil were spilled. When an incident of this magnitude occurs, we want a detailed, comprehensive root cause analysis investigation. First, let's look at the root cause analysis you would get using media headlines. First headline is Tanker spills 10.8 million gallons of oil. Here, we have an impact to the environmental goal because of the oil that has been spilled. Our second headline, tanks rupture and release oil when a ship grounds on Bligh Reef. The cause of the oil being spilled was 8 cargo tanks being ruptured. The tanks were ruptured because the ship grounded on Bligh Reef. And our last headline, tanker captain legally drunk during spill. If you've heard anything about the Valdez oil spill, this is probably what you've heard, that there was alcohol in the captain's system at the time of the grounding. Conclusions were thus made that the ship grounded because the captain is drunk. Our resultant cause map, made based only on headlines, shows us that the oil is spilled because of ruptured tanks. The tanks ruptured because the ship grounds on Bligh Reef, and the ship grounds because the captain had alcohol in his system. The solution, then, is to fire the captain, which in this case did happen fairly shortly after the incident.
Okay, so we did a quick analysis. We came up with a solution, fire the captain. Is the problem solved? Okay, and you're absolutely correct. The problem is absolutely not solved, and whether firing the captain was the right thing to do or not, you know, that's up for an investigation and interpretation. Why is alcohol allowed? That's a great question. By international law, a captain of a vessel, of a commercial vessel like this, an oil tanker, what do you think the legal blood alcohol content level is for this captain? Like for driving a car in most states, it's 0.8. Okay, so what do you think it is for this captain? Or 0.08, excuse me. What do you think it is for this captain? .4? Just because he's a captain, right? Okay, the legal, and by international law, the legal blood alcohol content is 0. Okay, and so it's just like piloting aircraft. He should have had exactly a blood alcohol content of 0. And so having any alcohol in his system while assigned as the captain of this vessel, he was in the wrong. Now, the only exception to that is if there was 2 qualified captains on this vessel, and he was in an off-duty status because the other captain was on duty, and then by the time that he returned to being on duty, he was at a blood alcohol content of 0.
As previously mentioned, for an incident of this magnitude, we need to have a detailed, comprehensive investigation. Let's look at the cause map that we would get if we based it on the detailed government reports. I know you can't see the cause boxes, but this is a 115 cause box cause map that outlines details about the Valdez oil spill. The yellow boxes on this map are the boxes from our previous 5-box cause map. You'll see they now make up only a small portion of the cause map, and there's a great amount of additional detail that has been added. Here we are back to our 5-box cause map. We can add detail before, after, and between the cause boxes. These first 3 causes seem to fit pretty well. Our environmental goal is impacted because 10.8 million gallons of oil were spilled, and the oil was spilled because 8 oil cargo tanks ruptured. However, let's look at the relationship here. The ship grounding on Bligh Reef caused the 8 oil cargo tanks to rupture. Let's see if we can add some detail in between these causes. The 8 oil cargo tanks ruptured because of force applied to the hull and because of inadequate hull strength.
Okay, when you're doing cause mapping, if you're going to have an and or any type of conjunction, you need to separate out the paths. And the reason is because, like with this situation, we got the 8 cargo tanks ruptured because force applied to the hull and inadequate hull strength. And we want 2 different paths here because we need to continue asking why going in this direction, and we need to continue asking why going in this direction. Now, here's a good question. The tank's ruptured, okay? That seems to be a result right now, okay? And then what was it caused by? Well, it was caused by this and it was caused by that. And so from relationship of our observation at this point, this is a cause and this is an effect.
Whenever something fails, it's because the forces applied are greater than the strength. In this case, the force on the hull was provided when the ship grounded on Bligh Reef.
Now, because I took my investigation further, now this is a cause and this is an effect, all right? Where previously it was a cause. And what point am I making here? Whether something is a cause or effect it depends on where you're at in your point of investigation. Are you looking to the right or are you looking to the left? Are you looking before something happened or are you looking after something happened? And so the discipline that we're following here with cause mapping is a cause is an effect and effect is a cause. It matters which direction I'm doing my analysis.
The inadequate hull strength was because of a single-hulled ship design. A solution that has been considered after the Valdez incident is to have double-hulled ship. This is what our cause map looks like with the additional detail that we've just added. Let's look at the last relationship from our original cause map. This implies that a drunken captain steered a ship into the reef. This graphic shows Prince William Sound with the north and southbound traffic lanes. The green indicates the southbound traffic lane, and this is the direction that the Valdez would have been headed. The red indicates the northbound traffic lane. You can see the original plan for the Valdez would be to travel along the southbound traffic lane. The yellow shows the route of the Valdez. As you can see, it began in the southbound traffic lane, crossed over all traffic lanes, and well out of the traffic lanes before it grounded on Bligh Reef.
Okay, so does that tell you a lot of new information? Does this map tell you a lot of good, valuable information? Absolutely. And so should it be available in our analysis? And the answer is absolutely yes. Now, here's an interesting question. It crossed over this sea lane. Well, what does that mean? This is a traffic lane where maybe a Princess cruise liner, could have been traveling with thousands of passengers on board, and this huge oil tanker just would have went broadsided it directly there, and I'm sure that probably would have had the tendency to sink that cruise liner as it was vectoring towards Bligh Reef here. Okay,
and so of the traffic lanes before it grounded on Bligh Reef.
On our cause map, what we're going to have the opportunity to do is put that detail in here.
Bligh Reef. The ship grounds on Bligh Reef because the vessel is outside normal traffic lanes, as we saw from the map on the previous slide. Additionally, the crew didn't realize the ship was too close to the reef. We know this is true because the ship didn't slow. We'll look at each of these causes in turn. First, let's look at why.
Okay, so here we had this evidence tag, and if I hadn't cut it off earlier, you would have seen an evidence tag populate on the ship grounds, and it showed that first map. But now we know that it didn't slow down. Why? Because of the accident investigation that took place. Well, when we have an evidence tag like this, if we're doing it on the wall, then we create a legend on here. It says evidence ship did not slow down, and you would call that like E1, E2, E3, evidence tag 1, 2, 3, whatever. And over on the wall, you would put, you would hang on the wall the accident investigation for documentary evidence. When you put this into an electronic format, this would be hyperlinked to where that accident investigation is. Same thing with that map previously. it would gain an evidence tag, and then you would hyperlink to where that's at.
The vessel was outside normal traffic lanes. The vessel was outside normal traffic lanes because the ship was attempting to avoid ice. This is something that a lot of people don't know about when they look at the Valdez incident. Let's look at this map again. We have our traffic lanes and the route of the Valdez, but this is just showing the map of Prince William Sound, not the actual situation on the day of the Valdez grounding. Instead, Prince William Sound looked like this. As you can see, the glacial ice.
Okay, so now we need the first map, just showing where the sea lanes are, but now we need to know what were the exact circumstances on the day that this Exxon Valdez crashed, and why did it leave the sea lanes? Well, because there was an ice formation, there was a glacial ice formation sticking out here into the sea lane, and so it was trying to avoid that ice. And so again, this is a very important part of the root cause analysis. Now I need to be able to call this, evidence 3 and hyperlink to it, or if we're doing it on the wall, then you put it over there on the wall, so people are bringing that into their more full understanding of what's going on.
Ice covered both the southbound and northbound traffic lanes and quite some distance outside both traffic lanes. So the Valdez was forced to leave both traffic lanes in order to get around the glacial ice. In addition to attempting to avoid ice, there was no warning to the ship from the vessel traffic center. The vessel traffic center would ordinarily provide a warning to a ship as they left the traffic lanes. Part of the reason for this was that the vessel traffic center lost radar contact, and the vessel traffic center procedures were not followed. As we have mentioned many times in our webinars, we never stick with procedure not followed. We'll just add a question mark.
For now, because we need to gain access into this third-party location and find out exactly why procedures were not followed and what procedures weren't followed and what's the solution for that. But what you're starting to pick up here is not only was there an ice formation, but there was no warning from the vessel traffic center because they lost contact because they didn't follow procedures. And so do we need one solution, fire the captain, or do we need a whole suite of solutions? And the answer is the latter. We need a collection of solutions. Just like a lot of your real world problems, they don't need a solution. They need a collection of solutions. So we need a mapping format that allows us to dig effectively and very visually.
Following this procedure is not followed, so that we know that some more detail needs to be added to this area of the map. One of the solutions implemented after this incident was to increase the number of radar sites, allowing the vessel traffic center to be able to better track vessels via radar. Now this portion of the cause map looks like this. We're going to add some detail onto why the crew didn't realize the ship was too close to the reef. The crew didn't realize the ship was too close to the reef because the position of the vessel was plotted incorrectly. The cause of the position of the vessel being plotted incorrectly was that the third mate was plotting and supervising. That meant that he plotted the position and verified that the position was correct. The reason that the third mate was performing both jobs was because of a reduced crew complement on the Valdez. In addition to this, the third mate was fatigued, again because of the reduced crew complement. In addition to the position of the vessel being plotted incorrectly, there was no radar indication of the reef. The reason for this was that the radar equipment on the Valdez was broken.
What? Yeah, I hear you, Kristen. What? How could this be? How could you be operating an oil tanker on the open seas with a broken radar? You want to talk about the perfect storm of things going absolutely catastrophically wrong. The traffic center lost radar contact because they didn't follow procedures. Now on board the Exxon Valdez itself, the radar is broken and they're still underway. They're still traveling the seas with a broken radar. How long has that been broken? Why isn't there redundancy for a mission critical piece of equipment? Why don't they have protocols, and why wouldn't those protocols be followed that if they have a broken radar, that they have to immediately get out of the sea lane? Okay. they did not have a quality team to do a ship walkthrough. You know, absolutely. So again, you know, it's just this unbelievable collection of errors and mistakes and misjudgments and bad procedures. And so again, you know, what I'm stressing is we need a system, a format, a tool,
One last issue.
a way to investigate where we can do this in a very robust manner. And where you see this evidence, I don't want to just go to the source documentation, or where you see the you know, what the solution is. They put a green tag at the top. I don't want to know that that's just the solution.
Was not on the bridge. In this case,
I want to know the how, you know, part of the solution. If you're going to tell me, hey, you know, fix the radar, I want to know the how associated with how it's going to be fixed. But more than just fixing the radar, I want to know, how are we going to control not having an oil tanker operating in international waters without a radar? Okay, and so yeah, they were testing the functionality by hitting something. I like that. Okay, I'm getting a call from Arizona. Is that one of you? Let me know if one of you are calling me from Arizona right now on my phone. Okay, it may be somebody that we've lost contact with during the course here. So let me just check this number real quick while you finish watching this.
Captain had alcohol in his system, which probably played into his decision not to be on the bridge. I do want to point out that the captain was found not guilty of piloting a vessel while intoxicated. We can add some solutions at this point that would have mitigated the risk of this Valdez oil spill. One of the solutions is not to transit the Prince William Sound at night. There's also a solution to require 2 watch officers on duty at all times. Another solution is to increase the crew size. A solution when you have equipment that is broken that is necessary for your ship to function is to fix the equipment. So another solution that we have is fix the radar. Going back to the 5-box cause map that we created based on media headlines, you will see if we had stopped at this oversimplified cause map, we would have missed the opportunity to make meaningful changes. Although it makes for a good sensational story to sell newspapers, it is not a solid cause and effect explanation. Blame, as has been doled out in the media for this incident, isn't going to help you solve the problem. Blame instead may lead you to fire the person that is deemed responsible for the incident. But by doing this, you may deprive your organization of a person who is best able to help you figure out what went wrong and fix it.
Okay. And so, yes, there's a whole lot going on there. And, you know, one thing that Jorge pointed out here is, you know, maybe they were trying to navigate by the stars, you know, like I told you, the United States Navy can do, but it's daylight and they couldn't see the stars. And by the way, if the Navy is going to turn off its radars and things of that nature, it's with intention and it's by design. And oh, by the way, it's because we have all the safety systems, including qualified and certified people to navigate in using different methods of navigation. And we also have satellites and aircraft and submarines that are watching over and safeguarding that ship's movement. But as far as, you know, navigating by the stars, those are signalmen. Signalmen would be in place, or quartermasters would be in place, and you would have a dozen people, you know, on that duty, on that tasking, you know, just to provide for the safe voyage. And oh, by the way, this is all very high qualified, highly certified, you know, people. And so it's with this oil tanker not having those type of systems of control and safety net and things of that nature, there's absolutely no reason why this oil tanker should be on the open seas without a radar. And so So hopefully what you picked up out of this is, yeah, we can start a conversation with root cause analysis using the Ishikawa fishbone diagram, but we're never really going to get to the comprehensive level that we can get using cause mapping here. Now, there is software that's available for cause mapping, specifically designed for cause mapping. This is really easy to kind of replicate if you wanted to capture this electronically using things like CorelDRAW and things of that nature. Or you could even replicate it, just using some very basic Microsoft tools. The advantage that you have with using software is it's already going to position those boxes for you. You don't have to spend time trying to be a graphic artist. And it will, if you put a solution at the top or evidence at the bottom, it's already prepared to receive the hyperlink, for the documentation that you want to add to that. And so, it's nice if you're going to do the cause mapping to have the appropriate software, but you can very much do it without the software. And can you do it on the wall? Absolutely. And often you should start off, doing it on the wall with sticky notes, with your full team. When you have documents to reference, just create a legend on your wall mapping and collect those over on the side. All right. Give me a TU if you like this Apollo method of cause mapping. Yes, it is. It's very cool, and it's a very robust tool for your analysis. And you'll notice I wasn't relying on a bunch of hypothesis tests and statistical analysis and stuff like that. Maybe some of what I need to do inside of this investigation, I need to have some of that in the background. But what I'm trying to tell you is you can do some very robust analysis with your problem area that you're doing a continuous performance improvement project on. You can do a lot of really helpful and robust analysis and come up with solution paths without high-end statistical analysis. And so having said that, we will say that certain things you are going to have to come back into this discussion about statistics and statistical analysis and looking at the probability of things and looking at descriptive statistics and inferential statistics. And so we're going to spend a lot of our time in the analyze phase, getting back to talking about data, talking about continuous distribution and tools and methods that we use for continuous distribution and tools and methods that we use in the analyze phase for discrete distribution of data. Okay, but before I take you any further, I told you I was going to take you into a hypothesis video, and so let me go ahead and bring that up for you. Sometimes this gets stuck. You say, Bob, I see all these funny videos and you haven't shown them all to us yet. Okay, so let me go ahead and send you another funny video. This one takes about 40 seconds. Okay, 42 seconds.
Hello, Laura, love. What are you doing there, then?
I'm burying my goldfish.
Oh, dear, what a shame. Still, it's only a goldfish, I suppose, isn't it? But why are you digging such a big hole, you silly thing?
Because it's inside your cat.
Original content every day. Channel B.
Okay, so, you know, he was about to just pass on, but he decided to pause and ask that critical question. And when we're engaging the world around us and we're just kind of doing some observation, whether it's intended observation or just a casual observation, if something strikes us as being curious, it can be very helpful to go ahead and ask the question. Now, maybe he doesn't want his cat to be buried right now because he doesn't want his cat to be dead at the moment just because it ate this goldfish. But at least now he doesn't have to go out in the middle of the night and put up looking for a cat wanted posters and all that kind of stuff. All right. At least now he has enough information to know where his cat's at. All right. And yes, I had to try and make a teaching point out of it. Okay. It is funny. It's a funny video. All right, so here we go into this fun topic of hypothesis testing. And these are, what I have for you is I have 2 videos as an introduction to hypothesis testing. And as I looked at your pre-assessments to this course, what I see is we have a different range of experience and confidence level with statistics and statistical analysis. So these videos may bore a couple of you that have very recently and very much in depth been using statistics and statistical analysis. And for others that it's been a while since you've been on that that wheel, it's going to be very helpful to refresh over this. And so what I'm going to do is I'm going to provide these links to you. I want you to verify the capacity to open both of them. Okay, and so that's the first one. So go ahead and give me a TU if you can open that one. And then let me pull up the second one. Good. Okay, and then this is the second one. And check this one as well. Give me a TU if you can open it. Give me a TD if you cannot open it. Kimberly, you cannot open it, but others can. Okay, you was just kidding. You was just checking to see if I was paying attention, wasn't you? I get it. Always testing me. All right. All right, so let me check the length of these again. Hold on. See what I'm putting you through.
Hello, welcome
Okay,
to
that one's
in Mastering Statistics. Here we're finally going to conquer the topic of hypothesis testing. It's one of the most central.
Okay, the first one is 23 minutes, and I think the one after that is, you know, okay, there it is, 14 minutes. Okay, so so that's actually about 40 minutes worth of viewing, and I was thinking that it was less viewing than that earlier, where I told you I was going to let you out at 4 to have time to watch those. We're going to go ahead and be closing down the class as a group right now. Now, what I would ask is if you have the opportunity, go ahead and watch those now independently so they don't get pushed off until morning, or try to get them watched sometime before this evening. I'm going to open up for questions here in just a second, Leanne. And so I am going to let you out early enough to watch 40 minutes worth of videos, because some of you may want to watch certain parts of it more than once. Okay, and so You got a 99% confidence level the link works. Okay, I get it. All right, Lanny, what was your question?
Hi, I just want to make sure, because when I clicked on the link, it takes me directly to like one video, not like the ones that we got yesterday, where like, you know, it went to like a folder and you had the.
Yeah. I sent you links to individual videos, and so you have 2 links, and so you should have access to 2 different videos. You good? Okay. All right, and like I say, those are long enough to where I feel like it would be most appropriate to go ahead and secure the class now. That'll take you to, if you go ahead and watch it right now, it's going to take you till probably about 4:30, you know, to get comfortable with those particular videos. Somebody tried to call me from Arizona earlier. I messaged and I haven't gotten a reply back yet, so maybe it's not somebody that's in the class. But if you need me to help you out in the observation or the analysis of either one of these videos, just give me a phone call. And if you have an email from me, you have my phone number, and because it's on the bottom of all of my emails. And so give me a phone call, give me an email, give me a text message, you know, however you want to contact me, and I will come in and help and support you in any questions that you have. But we will also review those those videos in the morning. There's a couple of points that I want to make out of each one of those. As you're watching these videos, I want you to think about what type of study that he's doing in these different types of videos. He's going to run a couple of hypothesis tests during the videos, and I want you to think about the type of study that he's running, and maybe some things that are good about the study, maybe some things that are bad about the type of hypothesis study. Particularly, I want on the second video where he's going to talk about student populations and making an analysis on students, I want you to particularly think about what are the chances of bias being introduced into the study that he's presenting. All right, and so with that challenge in front of you, I'm going to go ahead and open the floor for questions. Any questions that you have now before I release you? You enjoyed the M&M activity. Good. I appreciate it, Kim. Thank you. Thank you for your all's attention. And I think you're going to enjoy these videos. You know, take your time with them if you need to. And let me know if you need something. All right. You're free to go as a class. Anybody that has any additional questions on a one-on-one, you can stand by or give me a phone call. Thanks.